Light takes 9 hours to cross its surface. 9 hours, not the distance from Earth to Mars, not the space between galaxies, the surface of a single star. If you could somehow place our sun at the center of this object, it would vanish like a grain of sand dropped into the Pacific Ocean. You could fit more than 5 billion suns inside it. And yet this star, this impossible sphere of burning gas wider than the orbit of Saturn, should not exist according to the laws of physics we use to understand the universe. It has a name, Stephenson 218. A red hypergiant sitting 19,000 light-years away in the constellation Scutum, quietly defying every model astronomers have built to explain how stars are born, how they live, and how big they are allowed to grow. Because there is a limit to size in this universe. A hard boundary where gravity and radiation pressure lock into a war no star should survive. Cross that line and the star begins to bleed. Not metaphorically, literally shedding mass into space, bleeding light and metal in violent pulses that shake the fabric of space-time itself. And Stephenson 218 is not alone. There is an entire class of stars out there, hypergiants, burning so hot and so fast that they should collapse under their own weight or tear themselves apart within a few million years. Some of them pulse like cosmic hearts, swelling and contracting every few hundred days. Some erupt without warning, hurling the mass of 10,000 Earths into the void in a single outburst. And some of them, the ones we are watching right now through our telescopes, died thousands of years ago. We just don't know it yet. So how does a star grow so large it breaks the rules, and why can't we explain it? Welcome to Magnetic Space. If you're new here, please subscribe. We make these documentaries every day, and honestly, we'd love to have you along for the ride. Before we begin, tell us in the comments where you're watching from and what time it is there. Now, settle in. This is going to be a good one. Light takes about 14.5 seconds to circle the sun. That's the distance around the star at the center of our solar system, the object that makes Earth habitable, the bright yellow disk you were taught never to stare at directly. 14.5 seconds at 300,000 kilometers per second, the fastest anything in the universe can move. That's the baseline, that's normal. That's what a star looks like when it behaves itself. Now imagine a star so absurdly, offensively large that light, moving at its absolute cosmic speed limit, would take 9 hours to make the same trip. Not 9 minutes, not 90 minutes, 9 hours. You could wake up, eat breakfast, go to work, sit through an entire shift, and light would still be crawling across the surface of this thing, trying to get back to where it started. That is not a star. That is a violation. The object in question is called Stephenson 218, and it sits roughly 19,000 light-years away in the constellation Scutum. It is one of the largest known stars in the observable universe, though the title keeps changing hands depending on whose measurements you trust and which year you're reading the paper. Some estimates put its radius at around 2,150 times the radius of our Sun. Other measurements are more conservative. The uncertainty itself is part of the story, and we'll come back to that. But for now, let's stay with the number that gets thrown around most often: 2,150 solar radii. A ball of hydrogen and helium so large that if you placed it where our Sun currently sits, its outer layers would extend past the orbit of Saturn. Not to Saturn's orbit, past it. Saturn would be inside the star. Jupiter would be inside the star. Mars, Earth, Venus, Mercury, all of them gone. Swallowed whole by a glowing envelope of gas, so diffuse you could fly a spaceship through it, and barely notice the difference between being inside the star and being in interplanetary space. The density at the surface of a hypergiant like Stephenson 218 is lower than the air you're breathing right now, lower than what we'd call a laboratory vacuum. And yet somehow this wisp of almost nothing holds together under its own gravity and shines with the light of hundreds of thousands of suns. Let's be clear about what we're comparing. The sun is not small. You could fit about 3 million Earths inside it. If Earth were a marble, the sun would be a sphere roughly as tall as a person. It's huge by every measure that matters to a human standing on a planet's surface. We are ants living on a rock orbiting a furnace, but put the sun next to Stephenson 218 and it becomes the marble. If you built a scale model where Stephenson 218 was the size of a standard 2-story house, the sun would be about the size of a grain of sand sitting on the front step. Earth wouldn't even register. You'd need a microscope to see it. This isn't just big. This is a different category of object entirely, operating under physical rules so extreme that for decades scientists weren't sure stars this size could exist at all. And technically, we're still not sure. The math gets uncomfortable. Let's slow down and walk through the scale properly, because numbers this large stop meaning anything unless you drag them into human terms. Start with Earth. Diameter roughly 12,700 kilometers. You could drive around the equator in a car, and it would take you a few weeks if you didn't stop. Manageable, finite, a thing you could imagine completing. Now step up to the sun. Diameter roughly 4 million kilometers. You can't drive around that, you can't walk it, you can't even conceptualize it in terms of human movement, but light can. Light circles the sun in 14.5 seconds, and that gives you a handle to grab onto. Light is fast. Light crosses the space between Earth and the Moon in a bit over a second. So when light takes 14 seconds to loop the sun, you understand that the sun is large, but the time frame is still something your brain can process. 14 seconds is how long it takes to read a couple of sentences out loud. Now make the jump to Stephenson 218. Light takes 9 hours. That's 540 minutes, 32,400 seconds. More than 2,000 times longer than the trip around the sun. If you tried to drive a car around Stephenson 218 at highway speed, assuming you could somehow survive and the surface didn't keep expanding and contracting as the star pulsates, you'd be driving for roughly 15,000 years. That's longer than all of recorded human history. Longer than agriculture. Longer than cities. You'd start your road trip before the pyramids were built, and you wouldn't finish until the present day. And that's just the perimeter. The volume is worse. Volume scales with the cube of the radius. If you double the radius, you don't double the volume, you multiply it by 8. Stephenson 218 has a radius about 2,150 times larger than the Sun. Cube that, and you get a volume roughly 10 billion times greater. 10 billion suns could fit inside this star, not pressed together, just floating in the space it occupies. You could stack solar systems inside Stephenson 218 the way you stack shipping containers in a warehouse. Entire planetary orbits, whole families of worlds circling their parent stars, all of it fitting comfortably inside a single object that still somehow qualifies as a star under the definition astronomers use. The definition, by the way, is surprisingly simple. A star is an object massive enough that the pressure and temperature in its core ignite nuclear fusion. Hydrogen atoms smash together under the weight of all the material pressing down from above, fuse into helium and release energy. That energy pushes outward, balancing the inward crush of gravity. As long as that balance holds, you have a star. It doesn't matter if the star is small and red and dim, or large and blue and blazing, or so grotesquely swollen that light takes half a workday to cross it. If fusion is happening in the core, it's a star. Stephenson 218 is still fusing hydrogen, barely. It's near the end of its life, puffed up to absurd size because it's running out of fuel, and the core is starting to contract while the outer layers expand. This is what happens to massive stars when they age. They don't shrink, they bloat. They become red supergiants or hypergiants, objects so large and so unstable that their outer atmospheres are barely bound to the core at all. Stephenson 218 is losing mass constantly, shedding material into space in a stellar wind so thick that if you could see it from a few light years away, the star would look like it was surrounded by a glowing fog. That fog used to be part of the star. Now it's drifting into the void, and it's never coming back. This is where things get strange. You'd think an object this massive would hold onto its material with an iron grip. Gravity should be crushing, and it is, deep in the core. But out at the surface, 2,150 solar radii away from the center, gravity is so weak that the star can't hold itself together. The outer layers are too far from the core. The radiation pressure from all the light being generated below is pushing outward so hard that it's literally blowing the star apart. Slowly, gently, but constantly. Stephenson 218 is not a stable object. It's a dying giant in the process of tearing itself to pieces, and the only reason it hasn't exploded yet is that the process is slow enough that we can watch it happen over thousands of years instead of seconds. How do you even measure a star like this? You can't walk up to it with a ruler. You can't send a probe. The star is 19,000 light-years away, which means the light you're seeing left its surface 19,000 years ago, back when humans were still painting on cave walls. What you're measuring isn't the star as it exists now. It's the ghost of what the star looked like when mammoths were still wandering the Earth. And you're measuring that ghost using instruments that are, at their core, just very sophisticated light detectors. Astronomers use a technique called interferometry, which combines the light from multiple telescopes to create a much sharper image than any single telescope could manage alone. They also use infrared observations because hypergiants like Stephenson 218 are cool by stellar standards, radiating most of their energy in wavelengths our eyes can't see. Then they estimate the distance to the star, calculate how bright it would appear at that distance based on how bright it looks from Earth, and use that to work out how large the star must be to produce that much light. Every step in that chain involves assumptions. Every measurement has error bars, and the error bars on something 19,000 light-years away are not small. That's why the title of largest known star keeps changing. In 2012, astronomers thought it was NML Cygni. Then UY Scuti took the crown for a while. Then Stephenson 218 showed up. Some papers still argue for UY Scuti. Others have thrown out candidates like WAHG64 or RW Cephei. The problem is that all of these stars are variable. They pulse, they expand and contract over months or years. They're surrounded by thick clouds of dust that make it hard to see where the star ends and the surrounding material begins. And they're all so far away that getting a clean measurement is less like taking a photograph and more like trying to guess the size of a building by looking at a blurry smudge of light on the horizon at midnight. UY Scuti, for context, is often listed at around 1,700 solar radii, though some older estimates put it much larger and some newer ones put it smaller. If that number holds, light would take about 7 hours to circle it. Still absurd. Still in the same ballpark as Stephenson 218. The point isn't to crown a winner. The point is that stars this large exist at all, and that existence is barely permitted by the laws of physics. There's a limit to how big a star can get. Astronomers call it the Eddington limit, named after Arthur Eddington, the British astrophysicist who worked it out in the 1920s. The idea is simple. A star generates energy in its core through fusion. That energy has to escape, and it does so in the form of light, photons streaming outward from the center. Photons carry momentum. When they slam into atoms in the outer layers of the star, they push. If the star is luminous enough, the outward pressure from all those photons can exceed the inward pull of gravity. When that happens, the star's outer layers get blown away. The star can't hold itself together. The Eddington limit sets a maximum luminosity for a star of a given mass. Go beyond that limit and the star shreds itself. Most stars sit comfortably below the limit. Our sun is nowhere close. But hypergiants are dancing right on the edge. Some of them are probably over the edge, held together only by the fact that they're losing mass so quickly that they keep dropping back below the threshold before they can fully disintegrate. They're not stable objects, they're controlled explosions. Stevenson 218 is losing mass at a rate of about 1/10,000th of a solar mass per year. That doesn't sound like much until you realize it's been doing that for thousands of years and will keep doing it until there's nothing left to lose. In a few 100,000 years, maybe a million, the core will run out of fuel entirely, collapse in on itself, and the star will explode as a supernova. Or maybe it won't. Stars this massive might be so unstable that they skip the supernova phase entirely and just collapse straight into a black hole, snuffing out without a final blaze. We don't know. We've never watched one die. They're too rare. And that's the other thing. These stars are not common. The Milky Way contains somewhere between 100 and 400 billion stars, depending on whose count you trust. Of those, only a few dozen are hypergiants, maybe fewer. The exact number is hard to pin down because we can't see the whole galaxy and because hypergiants don't last long. A star like the Sun will burn for about 10 billion years. A hypergiant burns out in a few million. Blink and you miss it. On cosmic timescales, hypergiants are mayflies. They form from the most massive clouds of gas in regions where star formation is running at full throttle. They ignite fast, burn hot, swell to monstrous size, and die young. By the time we spot them, they're already near the end. Stevenson 218 isn't a young star figuring out how to be big. It's an old star in its death throes, and the size we're seeing is a symptom of that death. It wasn't always this large. When it first formed, it was probably a blue supergiant, smaller, hotter, more compact. As it aged and exhausted the hydrogen in its core, it expanded. The core contracted and heated up, igniting helium fusion. The outer layers, no longer supported by the same intense radiation pressure from hydrogen fusion, drifted outward. The star bloated. And now it's here. A red hypergiant so large that it defies intuition and sits at the ragged edge of what stellar physics allows. There's a part of your brain that wants to ask why we should care. It's far away. It's not going to hurt us. It's just a big ball of gas doing what big balls of gas do. But the reason we care is the same reason we care about any extreme. Hypergiants are stress tests. They're the places where the rules get pushed so hard that they start to bend, and when the rules bend, we learn where they actually come from. Every star we've ever studied, including the Sun, follows a script written by gravity, fusion, and thermodynamics. Hypergiants follow the same script, but they're performing it at a volume so loud that the edges of the stage are starting to crack. If we want to understand what stars are really capable of, we have to study the ones that are barely holding it together, and we're just starting to get the tools to do that. For most of human history, stars were points of light. Then they became objects with measurable properties. Then we figured out what they were made of, how they burned, how they evolved. Now we're at the stage where we can measure the size of individual stars across thousands of light years, map their surfaces, track their pulsations, watch them lose mass in real time. Stevenson 218 isn't just a curiosity, it's a laboratory. A place where the universe is running an experiment on its own rules, and we get to watch. The 9-hour star is real. It's out there right now, glowing faintly in the infrared, shedding material into the void, ticking down toward an end we can predict but not prevent. It shouldn't exist under the tidy models we built in the 20th century, but it does. And the fact that it does means our models were incomplete. Not wrong, just incomplete. There are corners of the universe where things get bigger, stranger, more extreme than we thought possible. Hypergiants are one of those corners. And now that we've found them, the question isn't just how they got so big. The question is what else we've been missing. Stevenson 218 is not alone. That's the part that should bother you more than the size itself. If there were only one star that broke the rules, you could write it off as a fluke, a cosmic accident, the universe having a weird day. But there are others. Dozens of them scattered across the galaxy, each one sitting at the edge of what physics says should be possible. And once you start looking at the full roster of hypergiants, a picture emerges. These stars aren't accidents. They're the inevitable result of a specific set of conditions playing out in the most extreme environments the universe has to offer. Let's meet the family. Start with Betelgeuse, because it's the only hypergiant most people have heard of. It's the red giant marking the shoulder of Orion, the Hunter constellation visible from almost anywhere on Earth during winter months in the northern hemisphere. You've probably seen it, bright reddish, sitting up and to the left if you're looking at Orion's belt. It's one of the few stars whose color is obvious to the naked eye, and that color is a warning sign. Red means cool by stellar standards, and cool means old and swollen. Betelgeuse sits about 650 light-years away, close enough that we've been able to study it in detail for decades. Its radius is somewhere around 764 times the radius of the Sun, though that number shifts depending on who's doing the measuring and when. Betelgeuse pulsates. It swells and contracts over a period of roughly 400 days, and during that cycle, its brightness changes noticeably. In late 2019 and early 2020, it dimmed so dramatically that astronomers started speculating it might be about to explode. The internet got excited. Articles were written, social media filled with predictions. Betelgeuse was going supernova, and we were all going to get front-row seats. It didn't explode. The dimming was caused by a massive cloud of dust ejected from the star's surface, blocking our view. The dust eventually cleared, and Betelgeuse went back to doing what it had been doing for thousands of years, which is slowly dying while the rest of us watch. But the panic was understandable because Betelgeuse is legitimately near the end of its life. Current estimates put its mass somewhere between 11 and 20 times the mass of the Sun. It's already burned through the hydrogen in its core and moved on to fusing helium. Eventually, it will fuse carbon, then oxygen, then silicon, each stage happening faster than the last. When it runs out of fuel entirely, the core will collapse and the star will explode in a supernova bright enough to be visible during the day from Earth. That could happen tomorrow. It could happen 100,000 years from now. On human timescales, the uncertainty is maddening. On cosmic timescales, it's already happening. If you replaced the Sun with Betelgeuse, Its outer layers would extend past the orbit of Mars. Earth would be inside the star, so would Venus and Mercury. The three inner planets of our solar system would be vaporized, absorbed into a glowing envelope of gas, so thin you could see through it, but so hot it would disintegrate anything solid in seconds. And Betelgeuse, as large as it is actually on the smaller end of the hypergiant scale. It sits right at the boundary between red supergiant and red hypergiant, depending on whose classification system you use. Some astronomers call it a supergiant, others bump it up a category. The distinction matters less than the fact that Betelgeuse is a nearby example of a star in the process of tearing itself apart, and we've been able to watch that process in more detail than almost any other object in its class. In 2009, astronomers used the Very Large Telescope in Chile to create the first direct image of Betelgeuse's surface. Not a point of light, an actual resolved disk showing bright spots and dark regions where convection cells were churning beneath the photosphere. That was the first time anyone had seen the surface of a star other than the Sun. The image wasn't sharp by the standards of, say, a photograph of Mars, but it was enough to show that Betelgeuse has weather. Massive bubbles of hot gas rising from the interior, cooling and sinking back down, each bubble larger than the entire Earth. The star is boiling. Now step up to something bigger. VY Canis Majoris. This one sits about 3,900 light-years away in the constellation Canis Major, the big dog chasing Orion across the winter sky. For a long time, VY Canis Majoris held the title of largest known star, though, like all hypergiant measurements, the numbers kept shifting as better data came in. Current estimates put its radius at roughly 1,500 times the radius of the Sun. Some older papers claimed it was larger. Some newer observations suggest it might be smaller. The uncertainty is baked into the process because VY Canis Majoris is surrounded by a thick nebula of dust and gas that it's been ejecting for thousands of years, and that material makes it nearly impossible to see where the star ends and the cloud begins. If you could see VY Canis Majoris up close, it wouldn't look like a clean sphere. It would look like a dying bonfire surrounded by smoke. The star itself is a deep red, radiating most of its energy in the infrared. The nebula around it glows faintly from the light of the star heating the dust. And embedded in that nebula are structures, arcs and knots and filaments of material that were ejected at different times and are now drifting outward at different speeds. Astronomers have mapped those structures using the Hubble Space Telescope, and what they found was chaos. No symmetry, no clean patterns, just a star hemorrhaging mass in every direction, blowing itself apart, one gust at a time. VY Canis Majoris is losing mass at an astonishing rate, somewhere around 30 times the mass of the Earth every year. That's not a misprint. Every year, this star sheds enough material to build 30 copies of the planet you're standing on. It's been doing that for at least 1,000 years, probably longer. The nebula around it contains several times the mass of the Sun, and all of that used to be part of the star. At the rate it's losing mass, VY Canis Majoris will be unrecognizable in another few thousand years. It might not even survive long enough to go supernova. It might just evaporate, leaving behind a naked core that collapses directly into a black hole without any fireworks at all. The mass of VY Canis Majoris is harder to pin down than its size, but most estimates put it around 17 solar masses. Notice that number, 17. Betelgeuse is somewhere between 11 and 20. Stephenson 218 is estimated at around 16 to 20. These are not the most massive stars in the galaxy, not even close. There are stars out there with masses exceeding 100 times the Sun. But those stars are smaller, hotter, bluer, more compact. They're burning so fiercely that they haven't had time to swell up yet. Hypergiants are big, not because they're the most massive, but because they're dying. The mass they were born with has been partially blown away, and what's left is a bloated core struggling to hold onto an outer envelope that's barely bound by gravity. This is one of the most counterintuitive facts about hypergiants. The biggest stars by volume are not the biggest stars by mass. A blue supergiant with 50 solar masses might have a radius only 20 or 30 times that of the Sun. A red hypergiant with 15 solar masses can have a radius 2,000 times larger. Size and mass decouple completely at this scale. What matters is how far the star has progressed through its life cycle, how much fuel it's burned, how much mass it's lost, and how unstable the balance between radiation pressure and gravity has become. Move to another example, Westerland 126. This one sits inside a massive young star cluster called Westerland 1, located about 11,500 light-years away. The cluster is only a few million years old, which means every star in it is young by cosmic standards. And yet Westerland 126 is already a red supergiant or hypergiant, depending on the classification. Its radius has been estimated at over 1,000 solar radii, and its luminosity is more than 200,000 times that of the Sun. That's remarkable because stars this luminous should still be blue and compact. They shouldn't have had time to evolve into red giants yet. But Westerland 126 has. The explanation comes down to birth mass. Westerland 126 probably started out as one of the most massive stars in the cluster, weighing in at 40 or 50 solar masses or more. Stars that massive burn through their hydrogen fuel in just a few million years. By the time the cluster was 5 million years old, Westerland 126 had already exhausted its core hydrogen and begun the transition to helium fusion. The core contracted, the outer layers expanded. The star went from blue to yellow to red, swelling to hypergiant proportions in what amounts to a cosmic eye blink. And now it sits there, shining like a bloated ember, radiating more energy in a single second than the Sun produces in a week. Westerland 1 is a useful laboratory because the cluster contains multiple hypergiants and supergiants, all at roughly the same distance and roughly the same age. You can compare them directly without worrying about whether one is billions of years older or thousands of light years farther away. What those comparisons show is that hypergiants come in different flavors. Some are red, some are yellow, a few are blue. The color tells you the surface temperature, and the surface temperature tells you where the star is in its death process. Blue hypergiants are early. They've started to evolve off the main sequence, but they're still hot, still compact by hypergiant standards. Yellow hypergiants are transitional, caught in the middle of their expansion. Red hypergiants are late stage, fully bloated, losing mass at catastrophic rates. All of them are ticking clocks. None of them will last. Let's talk about what makes a hypergiant, because the definition isn't just about size. You can't point a telescope at a star, measure its radius, and declare it a hypergiant based on that alone. The classification is based on a combination of properties, luminosity being the most important. A hypergiant is a star with a luminosity above a certain threshold, typically somewhere around 100,000 times the Sun's luminosity, though the exact cutoff varies depending on the source. Luminosity is the total amount of energy a star radiates per second across all wavelengths. It's different from brightness, which is how much light reaches your eye. Luminosity is intrinsic. Brightness depends on distance. Hypergiants are among the most luminous stars in the galaxy. Some of them exceed 1 million solar luminosities. That level of energy output creates problems. Remember the Eddington limit. When a star's luminosity gets high enough, the outward pressure from radiation can overcome gravity. The star starts to blow itself apart. Hypergiants are operating right at that limit, and many of them are probably exceeding it intermittently. They're held together not by stable equilibrium, but by the fact that they're losing mass so quickly that they keep dropping back below the threshold before total disintegration can happen. The mass loss happens through stellar winds, which is a polite term for what's actually going on. The star isn't gently exhaling gas, it's hemorrhaging. High-energy photons streaming out from the core slam into atoms in the star's outer atmosphere, transferring momentum. The atoms accelerate outward. If the star is luminous enough, those atoms reach escape velocity and fly off into space, carrying some of the star's mass with them. The process is continuous. A slow, steady leakage that over thousands of years can strip away a significant fraction of the star's total mass. Stellar winds in hypergiants are some of the most powerful outflows in the universe. Wind speeds can reach several hundred kilometers per second. Mass loss rates can exceed 1/10,000th of a solar mass per year, which sounds small until you multiply it out over 1 million years and realize the star has shed an entire sun's worth of material. And the wind doesn't blow smoothly. It's clumpy, turbulent, full of shocks and instabilities. When you point a spectrograph at a hypergiant, you see broad emission lines and P Cygni profiles, spectral features caused by gas moving toward you and away from you at the same time. The star is surrounded by a shell of ejected material glowing in ultraviolet and infrared, and that shell is expanding outward at speeds that would cross the distance from Earth to the Moon in under an hour. Astronomers measure these winds using a combination of techniques. Ultraviolet spectra show absorption lines from ionized atoms in the outflowing gas. Optical and infrared spectra reveal emission lines from cooler material farther out. Radio observations detect free electrons in the wind. Infrared observations pick up thermal emission from dust grains that condense in the cooler outer regions of the outflow. Put all that data together and you can build a model of how much mass the star is losing, how fast it's moving, and what it's made of. What the models show is that mass loss is not optional for hypergiants, it's existential. The more luminous the star, the stronger the wind. The stronger the wind, the faster the star loses mass, and the faster it loses mass, the more unstable it becomes. It's a feedback loop. Some hypergiants are thought to experience episodic mass loss events, where they eject a huge chunk of material all at once, possibly triggered by instabilities deep in the envelope or by the sudden ignition of a new fusion process in the core. VY Canis Majoris might have gone through several of these events. Eta Carinae, another famous hypergiant, definitely did. In the 1840s, Eta Carinae erupted and briefly became the second brightest star in the sky, despite being more than 7,000 light-years away. The eruption ejected several solar masses of material in a matter of years, and the star is still surrounded by the debris. Finding these stars is harder than you'd think. They're extremely rare. The Milky Way probably contains fewer than 50 confirmed hypergiants, and that number might be generous. Most of them are hidden behind dust clouds or located on the far side of the galaxy, where distance and extinction make them nearly impossible to observe. The ones we know about were discovered mostly by accident during large-scale surveys that happened to catch a very luminous infrared source in a region of active star formation. Astronomers then followed up with spectroscopy to measure the star's temperature, luminosity, and mass loss rate. If all the numbers lined up, the object got classified as a hypergiant. Spectroscopy is the key. You can't measure a star's size directly unless it's very close and you have an interferometer. For distant hypergiants, you measure the spectrum, calculate the luminosity based on how bright the star appears and how far away it is, estimate the temperature from the color and spectral lines, and use a model of stellar atmospheres to work backward to the radius. The process is indirect, full of assumptions, and the error bars are large. That's why you get papers arguing over whether UY Scuti or Stevenson 218 or some other candidate is the largest. The measurements overlap within their uncertainties. The stars themselves are variable, pulsating and changing size over time, and the surrounding dust makes it hard to see where the star ends and the nebula begins. The surprising thing is not that we don't know exactly which star is largest. The surprising thing is that we know about any of them at all. These objects are so far away and so deeply embedded in their own ejecta that detecting them requires pushing telescopes to their limits. Infrared observations are essential because red hypergiants radiate most of their energy at wavelengths human eyes can't see. Dust that would completely block visible light is transparent in the infrared, so infrared telescopes can peer through the obscuring clouds and see the star underneath. That's how the 2-micron all-sky survey and the Spitzer Space Telescope found dozens of previously unknown red supergiants and hypergiants in the early 2000s. They were there all along. We just couldn't see them until we looked in the right wavelength. Another surprise is that hypergiants are not always the most massive stars in their clusters. Blue supergiants with 60 or 80 solar masses can sit right next to red hypergiants with 20, and the red one will be 50 times larger. That's because the red one is older in evolutionary terms. It was born with more mass, burned through its core hydrogen faster, and has already started the process of swelling and shedding material. The blue one is still on the main sequence, still fusing hydrogen in a stable core, still compact. Give it another million years and it will start to evolve too. Eventually it might become a hypergiant itself, or it might explode as a supernova before it gets the chance. The path a star takes depends on its initial mass, its composition, how much mass it loses along the way, and a dozen other factors that we're still trying to fully understand. Initial mass is the single most important factor. A star born with 10 solar masses will never become a hypergiant. It doesn't have enough mass to generate the luminosity required. It will live for a few 100 million years, swell into a red giant, shed its outer layers, and leave behind a white dwarf. A star born with 25 solar masses has a shot. It will burn faster, evolve into a supergiant, possibly a hypergiant if the conditions are right, and end its life in a supernova. A star born with 40 or 50 or 60 solar masses is almost guaranteed to pass through a hypergiant phase at some point, assuming it doesn't lose too much mass too quickly and skip straight to a Wolf-Rayet star, which is a whole different kind of nightmare. The hypergiants we see today are the ones that threaded the needle, massive enough to become luminous, evolved enough to have swollen up, but not so stripped by mass loss that they've already collapsed or exploded. They're survivors of a brutal selection process, and the fact that we can study them at all is a piece of luck. In a few 100,000 years, most of the hypergiants currently catalogued will be gone. New ones will form in their place, but we won't be around to see them. The universe's largest stars are transient. They exist for a blink, shine with absurd brightness, and then vanish. That transience makes them valuable. Every hypergiant is a snapshot of a star in crisis, a star losing the fight against its own luminosity. And because they're so unstable, they're also unpredictable. They flare, they dim. They eject shells of gas. They pulsate with periods measured in months or years. Betelgeuse's recent dimming event was a reminder that these objects can change dramatically on timescales short enough for humans to notice. Most astronomical processes happen too slowly to observe in real time. Hypergiants are an exception. They're changing fast enough that if you watch one for a decade, you'll see it do something. We've now mapped out a small gallery of monsters. Stephenson 218 with its 9-hour circumference, Betelgeuse, close enough to image its surface, VY Canis Majoris, wrapped in its own funeral shroud, Westerland 126, shining like a beacon from a cluster of newborns. Each one is a different snapshot of the same basic process, a massive star reaching the end of its fuel supply and responding by growing to a size that should not be mechanically possible. They exist because the universe allows them to exist, barely, and they tell us that there are regimes of stellar evolution where the normal rules bend so far they almost break. The question that lingers after you've stared at enough hypergiants is how they got that way in the first place. What makes a star massive enough to become one of these things? What happens in the core of a giant molecular cloud that allows some clumps of gas to collapse into 50 solar mass monsters while others peter out at half a solar mass and become dim red dwarfs? The formation process is where the story really starts. And to understand that, you have to go back to the beginning, to the clouds, to the collapse, to the moment gravity takes hold of a pocket of hydrogen and starts building something that will one day become larger than the orbit of Saturn. We need to go back to the beginning, not the beginning of one star, but the beginning of stars in general. To the cold, dark nurseries where hydrogen clouds collapse and something that wasn't alive in any meaningful sense suddenly switches on and starts burning. Because if you want to understand how a star ends up so large that light takes 9 hours to cross it, you first have to understand how stars grow massive in the first place. And the answer is not what most people assume. Stars are not built, they collapse. That's the first thing to get straight. Nobody assembles a star piece by piece. There's no construction crew, no blueprint. What happens is that somewhere in the depths of a giant molecular cloud, a region of space filled with hydrogen gas and trace amounts of helium and dust, gravity finds a weak spot, a place where the density is just slightly higher than the surroundings. Maybe a supernova shockwave passed through and compressed the gas. Maybe two clouds collided. Maybe the cloud just got large enough that its own gravity started to matter. Whatever the trigger, once the process starts, it feeds itself. The higher density region pulls in more gas from the surrounding cloud. That makes it denser. Higher density means stronger gravity. Stronger gravity pulls in more gas. The cycle accelerates. What started as a slight ripple in an otherwise uniform cloud becomes a collapsing knot of material falling inward under its own weight. At first, the collapse is slow. The gas is cold, only a few tens of degrees above absolute zero, and it's spread out over distances measured in light years. But as the material falls inward, it heats up. Gravitational potential energy converts to thermal energy. The center of the collapsing cloud starts to glow, first in the infrared, invisible to human eyes, then brighter as the temperature climbs. This is a protostar, not yet a star, but getting there. It's a hot, dense core surrounded by a thick envelope of infalling gas and dust. The core is contracting, heating up, but it's not yet hot enough or dense enough to ignite fusion. That requires conditions so extreme that hydrogen nuclei, which normally repel each other because they're both positively charged, get forced close enough together that the strong nuclear force takes over and fuses them into helium. The temperature threshold for that is around 10 million degrees Kelvin. The pressure required is crushing, and the protostar has to keep collapsing until it reaches those conditions. For a star the mass of our Sun, this process takes about 50 million years. For a star with 10 times the Sun's mass, it takes less than a million. For a star with 50 solar masses, the kind that will eventually become a hypergiant, the collapse happens in just a few 100,000 years, maybe faster. The more massive the collapsing core, the stronger its gravity, and the faster it heats up. Massive stars don't wait around. They form fast, ignite fast, and start burning through their fuel almost immediately. But there's a problem. As the protostar heats up, it starts radiating energy, a lot of energy, and that radiation pushes outward on the surrounding gas. Photons carry momentum. When they slam into dust grains or gas atoms in the envelope, they transfer that momentum and push the material away. If the radiation pressure gets strong enough, it can halt the infall entirely. The gas stops collapsing, the protostar stops growing, and you end up with a smaller star than you would have otherwise. This is why there's an upper limit to how massive a star can get. Above a certain mass, radiation pressure during the formation process becomes so strong that it blows away the infalling material before it can be added to the protostar. The star can't grow any larger because it's actively preventing itself from accreting more mass. Current models suggest that limit is somewhere around 150 to 200 solar masses, though the exact number is still debated. Stars heavier than that probably can't form under normal conditions. The radiation pressure is just too strong. But stars up to that limit can and do form, and when they do, they're monsters from the moment they ignite. A protostar with 50 solar masses collapses, heats up, reaches the fusion threshold, and suddenly the core ignites. Hydrogen starts fusing into helium, energy pours outward, the infall stops. The star stabilizes, and what you're left with is an object so luminous and so hot that it dominates everything around it. Let's talk about what fusion actually does, because this is the engine that runs the whole show. At the core of a newly formed massive star, the temperature is around 15 million degrees Kelvin, and the pressure is roughly 250 billion times the atmospheric pressure at sea level on Earth. Under those conditions, hydrogen nuclei are moving so fast and colliding so violently that occasionally two of them get close enough for the strong nuclear force to bind them together. When that happens, they don't stay as two separate protons. They fuse into a heavier nucleus, eventually producing helium after a chain of reactions. And when they fuse, they release energy. The energy comes from mass. The helium nucleus weighs slightly less than the sum of the hydrogen nuclei that went into making it. The missing mass has been converted directly into energy according to Einstein's equation. Energy equals mass times the speed of light squared. The speed of light is a very large number. Square it and it's enormous, so even a tiny amount of mass converts into a staggering amount of energy. A single fusion reaction releases only a tiny burst, but in the core of a massive star, trillions upon trillions of fusion reactions are happening every second. The cumulative energy output is beyond comprehension. That energy has to go somewhere. It starts as gamma rays, high-energy photons born in the core. Those photons begin traveling outward, but they don't get far. The star's interior is opaque. Photons scatter off electrons and ions, bouncing randomly in every direction. A single photon can take hundreds of thousands of years to work its way from the core to the surface, ping-ponging through the dense interior in a slow, random walk. As the photon travels outward, it loses energy. It gets absorbed and re-emitted at longer wavelengths. By the time it reaches the surface, What started as a gamma ray has been degraded into visible light or infrared, but the energy is still there. The star is glowing because fusion in the core is constantly pumping energy outward. For a star on the main sequence, the phase where it's steadily fusing hydrogen in its core, fusion energy creates an outward radiation pressure that balances the inward pull of gravity. The star is in equilibrium. Gravity wants to crush it. Radiation pressure wants to blow it apart. The two forces are equal, so the star just sits there, stable, burning fuel at a steady rate. Our sun has been doing this for about 4.5 billion years. It will keep doing it for another 5 billion. It's a remarkably stable arrangement. Massive stars don't get that luxury. A star with 10 solar masses burns hydrogen about 1,000 times faster than the sun. A star with 50 solar masses burns it tens of thousands of times faster. The reason is simple. Higher mass means higher core pressure and temperature. Higher temperature means faster fusion. Faster fusion means more energy output. More energy output means higher luminosity. A 50 solar mass star can be 100,000 times more luminous than the sun, and all that energy is being generated by burning through the same fuel. So the fuel doesn't last. The sun will spend 10 billion years on the main sequence. A 10 solar mass star spends about 20 million years. A 50 solar mass star might spend only a few million. For the most massive stars, the ones that will eventually become hypergiants, the main sequence phase is a sprint. They ignite, burn furiously, and exhaust their core hydrogen in what amounts to a cosmic instant. And once the hydrogen in the core runs out, everything changes. When the core hydrogen is depleted, fusion in the core stops. Suddenly there's no outward radiation pressure from fusion to counteract gravity. The core contracts. As it contracts, it heats up. The temperature rises enough to ignite hydrogen fusion in a shell surrounding the now inert helium core. The star is no longer fusing hydrogen in its center. It's fusing it in a thin shell around the center. And that shell fusion produces even more energy than core fusion did. The star's luminosity increases. This is where things get weird. You'd think that more energy output would make the star hotter. It doesn't. The outer layers of the star respond to the increased energy by expanding enormously. The core contracts and heats up. The envelope expands and cools down. The star swells to many times its original size. The surface temperature drops. The star's color shifts from blue or white to yellow and eventually red. A massive star that spent its main sequence life as a compact blue giant transforms into a red supergiant. If it's massive enough and the conditions are right, it becomes a red hypergiant. This is the phase where stars like Betelgeuse and Virine Canis Majoris and Stephenson 218 exist. They're not young stars figuring out how to burn fuel. They're old stars running on fumes. The hydrogen in their cores is gone. Shell burning has taken over. The envelope has expanded to a size that would swallow planets. And the star is losing mass at a catastrophic rate because the outer layers are so loosely bound that radiation pressure and stellar winds are blowing them off into space. Let's walk through what's happening inside one of these bloated giants, because the internal structure is nothing like what you see in a normal star. At the center, there's a core made mostly of helium. It's not fusing yet, it's just sitting there, inert, supported by electron degeneracy pressure, a quantum mechanical effect that keeps the core from collapsing further for the moment. Surrounding that core is a shell where hydrogen is fusing into helium. That shell is thin, maybe only a few % of the star's radius, but it's producing enormous amounts of energy. Above the shell is the envelope, a vast region of hydrogen and helium that's barely held together by gravity. The envelope can extend for hundreds of millions of kilometers. The density at the outer edge is lower than the best vacuum we can create on Earth. And yet somehow this structure holds together. It holds together because even though the outer layers are diffuse, there's still a lot of mass. A red supergiant with 15 solar masses might have shed a few solar masses over its lifetime, but it still has more than 10 solar masses of material in its envelope. That's enough for gravity to keep pulling inward, even if the pull is weak at the surface. The star is a balancing act. Radiation pressure from the shell burning pushes outward. Gravity pulls inward. The star expands until the two forces balance again, and the balance point is absurdly far from the core. Now the core keeps contracting. As it does, the temperature climbs. Eventually, it gets hot enough to ignite helium fusion. Helium nuclei fuse into carbon and oxygen. This process releases energy, but not as much energy per reaction as hydrogen fusion, and it happens much faster. A star that spent millions of years burning hydrogen will burn helium in only hundreds of thousands of years. Once the helium is exhausted, the core contracts again, the temperature rises again. If the star is massive enough, carbon fusion ignites, then oxygen fusion, then silicon fusion. Each stage releases less energy, happens faster, and produces heavier elements. The star is building up layers like an onion. A core of iron surrounded by a shell of silicon fusion, surrounded by a shell of oxygen fusion, surrounded by shells of carbon, helium, and hydrogen. Each layer burning its fuel and adding ash to the layer below. For a star massive enough to go through this entire sequence, the final stages happen terrifyingly fast. Silicon fusion, the last stage before the core becomes iron, lasts only a few days, then it stops. Iron doesn't fuse. Fusing iron consumes energy instead of releasing it. The moment the core turns to iron, there's no more fuel, no more fusion, no more outward pressure. Gravity wins. The core collapses in less than a second. The collapse is so violent that it triggers a supernova, and the star explodes. Everything outside the core gets blown into space at 10% the speed of light. What's left is either a neutron star or a black hole, depending on how much mass was in the core when it collapsed. But we're not there yet. We're still in the red supergiant or hypergiant phase, where the star has expanded to ludicrous size and is burning helium or carbon in its core while simultaneously losing mass through stellar winds. This is the phase where the star is biggest. And the reason it gets this big comes down to one thing. The envelope is no longer in thermal equilibrium. In a main sequence star, energy produced in the core gradually works its way outward through radiation and convection. The temperature drops smoothly from the core to the surface. The structure is stable. In a red supergiant, that smooth energy transport breaks down. The envelope is so extended and so cool that convection becomes inefficient. Energy gets trapped in the lower layers. The outer layers puff up even more. The star becomes a giant convecting mess with massive cells of hot gas rising and cool gas sinking, each cell larger than the orbit of Earth. Betelgeuse's surface imaging showed this, giant bright spots where hot material from below was rising to the surface. Dark regions where cooler material was sinking back down, the entire star boiling like a pot of water on a stove. Except the pot is 1,000 times wider than the sun, and the water is ionized hydrogen at several thousand degrees. The scale is absurd, and the structure is barely stable. This is where radiation pressure becomes critical. In a main sequence star, radiation pressure is important, but not dominant. Gravity is stronger. In a hypergiant, radiation pressure is strong enough to compete with gravity in the outer layers. Photons streaming out from the shell-burning region slam into atoms in the envelope and push them outward. For atoms of certain elements, especially metals like iron, the cross-section for absorbing photons is large. Those atoms get pushed harder, they accelerate outward, and they drag surrounding gas with them. The result is a stellar wind, a constant outflow of material from the star's surface into space. In the most luminous hypergiants, the wind is so strong that the star loses a significant fraction of its mass over just a few thousand years. VY Canis Majoris is losing 30 Earth masses of material every year. That's not a gentle breeze, that's a hurricane, and the wind is driven entirely by radiation pressure. The star is so luminous that its own light is blowing it apart. There's a theoretical maximum luminosity for a star, called the Eddington luminosity, where radiation pressure exactly balances gravity. Go above that limit and the star can't hold itself together. Most stars sit comfortably below the Eddington limit. Hypergiants are dancing right on the edge. Some might be exceeding it intermittently. When a star crosses the Eddington limit, the outer layers become unbound and get ejected into space. The star shrinks slightly, the luminosity drops below the limit, and the ejection stops. Then the star puffs back up, crosses the limit again, and ejects more material. The cycle repeats. The star is unstable, oscillating around the threshold where physics says it shouldn't be able to exist. And here's the thing, the bigger the star gets, the weaker gravity is at the surface. Gravity falls off with the square of the distance from the center. If you double the radius, gravity at the surface drops by a factor of 4. Stephenson 218 has a radius more than 2,000 times the Sun's. At its surface, gravity is millions of times weaker than gravity at the Sun's surface. It's so weak that even a modest amount of radiation pressure can overcome it. The star is barely holding on to its outer layers. A slight increase in luminosity, a convective surge that brings extra energy to the surface, and an entire shell of gas can be ejected. The star doesn't explode, it just leaks. This is the paradox of hypergiants. They're huge because they're dying because they're huge. The expansion reduces surface gravity to almost nothing. The low surface gravity makes it easy for radiation pressure to blow material away. Losing mass destabilizes the envelope further. The envelope expands more, gravity gets weaker. The cycle feeds itself until the star has shed so much mass that it either collapses into a denser configuration or explodes. There's no stable endpoint. Hypergiants are temporary. They exist because the transition from compact supergiant to exploding remnant happens slowly enough that we can catch them in the act. The stars that become hypergiants started out with something like 20 to 50 solar masses, maybe more. They spent a few million years on the main sequence as blue supergiants, luminous and compact. Then they exhausted their core hydrogen, ignited shell burning, and expanded into yellow supergiants. Then they expanded further and cooled into red supergiants. If they're near the upper end of the mass range and haven't lost too much material to stellar winds during their earlier phases, they expand even more and cross into hypergiant territory. The exact path depends on the star's initial mass, its chemical composition, and how much mass it loses along the way. Stars born in environments with more heavy elements, which astronomers call metals even though they include things like carbon and oxygen, lose mass more efficiently because metals increase the opacity of the outer layers and make radiation pressure more effective. Stars born in metal-poor environments hold onto their mass longer and might follow a different evolutionary track. What we're seeing when we look at Stephenson 218 or VY Canis Majoris is a snapshot. A moment in a process that started millions of years ago when a massive protostar collapsed out of a molecular cloud, and will end in a few 100,000 years when the core runs out of fuel and the star explodes. The giant size is not permanent, it's a phase. And the phase exists because the star has reached a point in its evolution where the core is contracting and the envelope is expanding, and the two are moving in opposite directions at the same time. The core will keep contracting and heating until it ignites the next stage of fusion. The envelope will keep expanding and cooling until radiation pressure blows it off entirely, or until the core collapses and triggers a supernova. Everything about these stars is a fight between gravity trying to crush them and energy trying to tear them apart. On the main sequence, energy wins just enough to keep the star stable. In the hypergiant phase, energy is winning too much. The star is overinflated, overluminous, losing mass it can't afford to lose, and held together only by the fact that the core still has a little bit of fuel left and gravity still has a little bit of pull. Take away either one and the whole structure falls apart, and yet they exist. They're out there, right now, glowing in the infrared, pulsing, ejecting shells of gas, ticking down toward an explosion we can predict but not prevent. The fact that stars can grow this large, can hold together at this scale, can maintain fusion in a core the size of Earth while the envelope stretches past the orbit of Saturn, is a testament to how precisely balanced the laws of physics are. Change the strength of gravity slightly, and stars couldn't form. Change the rate of fusion slightly, and they'd either explode immediately or never ignite. Change the way radiation interacts with matter, and hypergiants would blow themselves apart before they ever got this big. But the laws are what they are. Gravity pulls, fusion pushes, radiation pressure shoves. And under exactly the right conditions, you get a star so large that it takes light 9 hours to make a lap. A star that exists at the ragged edge of instability. A star that by every reasonable measure should not be able to hold itself together, but does anyway, because the universe allows it for just a little while longer. And in that little while, we've been lucky enough to notice, to measure, to study, to stare at something that shouldn't be possible and ask how the hell it got that way. The answer is gravity and fusion and time. The same ingredients that built every star in the sky, just pushed further, burned faster, stretched to a breaking point that hasn't quite broken yet. Now we need to talk about what happens when these stars start to come apart. Because hypergiants don't just sit there glowing quietly like well-behaved furnaces. They bleed, they pulse, they eject shells of superheated plasma into space at speeds that would cross the distance from Earth to the Moon in minutes. And they do all of this while barely holding themselves together against forces that should have torn them to pieces millions of years ago. This is where the physics gets uncomfortable. This is where stars stop following the script and start improvising their own violent exit. Let's start with a star that decided to throw a tantrum in front of the entire astronomical community. Rho Cassiopeia. It's a yellow hypergiant sitting about 8,000 light-years away in the constellation Cassiopeia. For most of recorded history, it sat there quietly, a faint yellowish star that only specialists bothered to watch. Then, in the summer of the year 2000, it erupted. Not a supernova. Not an explosion in the traditional sense. Something stranger. The star's outer layers suddenly ejected a massive shell of material into space. In the span of a few months, Rho Cassiopeia threw off roughly 3% of a solar mass. That's about 10,000 times the mass of Earth, gone, ejected into the surrounding void in what amounted to a stellar cough. Astronomers watched it happen in real time. The star dimmed dramatically as the ejected material expanded and cooled. Its surface temperature, normally around 7,000 degrees Kelvin, dropped to below 4,000 degrees in roughly 200 days. That's a temperature swing so extreme it would be like the sun suddenly cooling to the point where its surface was barely hotter than molten lava. For a star, that kind of change doesn't happen slowly over millions of years. It happened in less than a year. The star's spectrum shifted. Lines that had been stable for decades suddenly showed massive Doppler shifts, indicating gas moving outward at hundreds of kilometers per second. The atmosphere was tearing itself apart. This was not the first time Rho Cassiopeiae had done this. Astronomers went back through old photographic plates and found evidence of earlier outbursts, one around 1945, another around 1893. The star has a history of violence. It erupts on a roughly 50 to 60-year cycle, though the intervals aren't perfectly regular. Each time, it ejects a significant chunk of its outer envelope into space. Each time, it dims, cools, and then slowly recovers over the following years. The 2000 outburst was just the first one that happened after we had built instruments sensitive enough to measure what was actually going on. We got lucky. We caught a hypergiant in the act of hemorrhaging. The mass loss rate during that outburst spiked to about 5/100ths of a solar mass per year. To put that in context, the star's normal mass loss rate, the steady background leakage that happens all the time, is about 1/1,000,000th of a solar mass per year. During the outburst, the rate increased by 50,000 times. For a few months, Rho Cassiopeiae was shedding material at a pace that would strip away its entire remaining mass in just a couple of decades if it kept going. It didn't keep going. The outburst ended, the star stabilized, but the fact that it could lose mass that quickly, that violently, tells you something important about how unstable these objects really are. Normal stars don't do this. The sun loses mass through the solar wind at a rate of about 1/10 trillionth of a solar mass per year. At that rate, it would take the sun tens of trillions of years to lose a meaningful fraction of its mass. The sun will die of old age long before the solar wind strips away anything significant. Rho Cassiopeiae, by contrast, has probably lost several solar masses over the course of its life through a combination of steady winds and episodic outbursts. It was likely born with something like 30 or 40 solar masses. It's now estimated to have around 20. The missing mass is floating out there in space, a series of expanding shells marking every time the star lost its grip on its own outer layers. Why does this happen? The short answer is that hypergiants are operating so close to the edge of stability that even small disruptions in the interior can trigger massive consequences at the surface. Remember the Eddington limit. That's the point where the outward pressure from radiation equals the inward pull of gravity. For a star sitting exactly at the Eddington limit, it doesn't take much to tip the balance. A surge of energy from the core, a convective cell bringing extra heat to the surface, a temporary increase in opacity that traps radiation in the outer layers, any of those can push the star over the edge. Once that happens, the outer layers become unbound. Gravity can no longer hold them. Radiation pressure blows them away. The process isn't smooth. It's not like turning on a faucet. It's more like a dam breaking. Once the outer layers start to lift off, the mass loss accelerates. The escaping gas carries away energy, which cools the layers below. Cooler gas is more opaque. More opaque gas traps more radiation. Trapped radiation increases the pressure. Increased pressure pushes more gas outward. The feedback loop runs until the star has ejected enough material that the luminosity drops back below the Eddington limit and the outburst stops. What you're left with is a star that's slightly smaller, slightly less massive, and surrounded by a glowing shell of ejected material expanding outward at hundreds of kilometers per second. This is not a theoretical process, it's observed. Rho Cassiopeia's 2000 outburst was caught on spectrographs across the world. The data showed gas moving outward with velocities exceeding 100 kilometers per second. The ejected shell was rich in heavy elements, titanium oxide and other molecules that form in cool, dense gas. That material condensed into dust grains within months of being ejected, creating a thick cloud around the star that absorbed starlight and re-radiated it in the infrared. For a while, Rho Cassiopeiae was surrounded by its own fog, a shell of dust and gas glowing faintly as it drifted away from the star that made it. Over the following years, the shell expanded and thinned. Today it's still out there, a faint nebula marking the site of an eruption that happened more than 2 decades ago. The term that gets thrown around to describe this kind of event is eruptive mass loss. It's distinct from the steady stellar wind that all hypergiants experience. Steady winds are always there, a constant outflow driven by radiation pressure on atoms in the outer atmosphere. Eruptive mass loss is episodic. It happens in bursts, and the bursts can be catastrophic. Some hypergiants are thought to eject as much mass in a single outburst as they lose through steady winds over thousands of years. The star doesn't explode, it doesn't go supernova, it just sheds a layer. And then it keeps going. There's an analogy that scientists sometimes use, though it's more poetic than literal. They describe the surface of a hypergiant as bleeding. Not blood, obviously, plasma. Superheated ionized gas glowing with the light of its own internal energy. The idea is that the star's outer layers are so loosely bound and so violently heated by radiation from below that material is constantly being torn away. It's not a clean process, it's messy. The surface of a hypergiant is a roiling convective chaos. Giant cells of hot gas rise from the interior, reach the surface, cool, and sink back down. Each cell can be larger than the orbit of Earth, and when those cells reach the surface, they can punch through the thin outer layers and eject plumes of material into space. Imagine standing on the surface of a hypergiant if such a thing were possible, which it isn't because you'd be vaporized instantly, but imagine it anyway. The ground beneath your feet isn't solid, it's gas, thin, hot, ionized gas. The density is lower than the air you're breathing right now. You'd be standing in what amounts to a hot vacuum. Above you, the sky wouldn't be black, it would be glowing. Radiation from the deeper layers of the star would be streaming upward, heating the gas around you to thousands of degrees. And every few minutes or hours, a convective plume would erupt nearby. A column of plasma hundreds of thousands of kilometers wide rising from below, punching through the surface and spraying material outward at escape velocity. The plume would glow white-hot. It would expand as it rose, cooling and dimming until it dissipated into a cloud of gas drifting away from the star. And then another plume would erupt somewhere else, and another. The entire surface would be a field of geysers, each one firing superheated plasma into space. That's not far from what's actually happening. Hypergiants don't have smooth surfaces. High-resolution imaging of Betelgeuse showed a mottled, uneven photosphere covered in bright spots and dark regions. Those bright spots are convective cells bringing hot material to the surface. The dark regions are cooler areas where material is sinking back down. The whole star is boiling, and where the convection is most violent, material can be accelerated to escape velocity and ejected entirely. The star isn't bleeding in the sense of a slow, steady drip. It's bleeding in the sense of a surface so active and so unstable that chunks of it are constantly being ripped away and thrown into space. Now add pulsation. Because hypergiants don't just eject mass randomly, many of them pulse. They expand and contract rhythmically over periods ranging from weeks to years. The pulsation isn't like a heartbeat in any biological sense, but the analogy is hard to resist. The star swells, the surface moves outward, then it contracts. The surface moves inward. The cycle repeats. Each pulse can change the star's radius by a significant fraction. A 10% change in radius for a star the size of Stephenson 218 means the surface is moving outward and inward by distances larger than the orbit of Earth. That's not a gentle oscillation. That's a violent heaving motion driven by instabilities deep in the star's interior. The pulsations are thought to be driven by what's called the kappa mechanism. Kappa is a term for opacity, a measure of how easily light can pass through a material. In certain layers of a hypergiant's envelope, the opacity changes with temperature in a way that creates instability. When the gas in that layer heats up, it becomes more opaque. More opaque gas traps radiation. Trapped radiation heats the gas further. The pressure builds. Eventually, the pressure gets high enough that the layer expands. Expansion cools the gas. Cooler gas becomes less opaque. Radiation escapes. The pressure drops. The layer contracts. The cycle repeats. The whole envelope acts like a giant engine, expanding and contracting as energy pulses through it. During the expansion phase, the star's surface moves outward. The surface gravity drops. Material at the surface becomes even more loosely bound than it already was. If the expansion is strong enough, the surface velocity can exceed escape velocity. When that happens, the outer layers don't fall back down. They keep moving outward. They've been ejected. The pulsation has launched a shell of gas into space. This is one mechanism by which hypergiants lose mass. Each pulse sheds a little bit of the star's outer envelope. Over thousands of pulses, that adds up. Rho Cassiopeia's atmosphere was observed to be pulsating unusually after its 2000 outburst. The normal pulsation period had been disrupted. The star's outer layers were still settling back down after the violent ejection event, and the usual rhythm had been thrown off. Astronomers tracked the star for years afterward, watching as the pulsations slowly returned to something resembling their pre-outburst pattern. The data suggested that the outburst itself had been triggered by an instability in one of the deeper layers, possibly related to a sudden ignition or shutdown of a fusion shell in the core. The energy pulse propagated outward through the envelope, amplified by the kappa mechanism, and eventually reached the surface with enough force to blow off the outer layers entirely. Another famous example is V838 Monocerotis. This one isn't a yellow hypergiant like Rho Cassiopeia. It's harder to classify. But in 2002, it experienced one of the most dramatic eruptions ever recorded. The star brightened suddenly, dimmed, brightened again, and then dimmed again over the course of several months. Each brightening phase was accompanied by the ejection of a shell of material. By the time the eruption ended, V838 Monocerotis had become a red supergiant surrounded by expanding shells of glowing gas. The Hubble Space Telescope captured stunning images of the light echo as the eruption's light reflected off surrounding dust clouds, creating an expanding ring of illumination that looked like a cosmic ripple spreading outward through space. Nobody knows exactly what triggered V838 Monocerotis's eruption. The leading theories involve either a stellar merger, where the star consumed a companion or a massive planet, or an internal instability that caused a runaway thermonuclear event in the outer layers. Either way, the result was the same. The star ejected a significant fraction of its mass in a series of violent pulses, transformed from a relatively normal star into a bloated red giant, and left behind a glowing nebula marking the site of its outburst. The event was a reminder that stars near the upper mass limit don't just evolve smoothly, they lurch, they erupt, they do things we didn't think were possible until we watched them happen. The Eddington limit keeps coming up because it's the boundary that defines how luminous a star can be before radiation pressure tears it apart. The limit itself is straightforward to calculate. You take the star's mass, assume a certain composition, calculate how much radiation pressure is needed to balance gravity at the surface, and out comes a maximum luminosity. For a star with the mass of the Sun, the Eddington luminosity is about 38,000 times the Sun's actual luminosity. The Sun is nowhere close to its limit. It's safe, stable, well-behaved. For a hypergiant with 15 or 20 solar masses, the Eddington luminosity is proportionally higher, but so is the actual luminosity. Hypergiants are so luminous that they sit right at the limit or just below it. Some measurements suggest that during outbursts, hypergiants can temporarily exceed the Eddington limit. When that happens, the outer layers should be blown away immediately, and they are. That's what an outburst is. The star crosses the threshold, ejects material until the luminosity drops back below the limit and then stabilizes. The limit isn't a hard wall, it's more like a speed bump. Cross it and you lose control. Eject enough mass and you drop back below it. The star survives by shedding pieces of itself. The puzzle is that the Eddington limit is based on simplified assumptions. It assumes the star's atmosphere is smooth and homogeneous. It assumes radiation interacts with matter in a straightforward way. Real hypergiants are neither smooth nor homogeneous. Their atmospheres are clumpy. Their winds are full of shocks and instabilities. The opacity changes dramatically with temperature, and the temperature changes dramatically with depth. When you try to apply the Eddington limit to a real hypergiant, the calculation gets messy. Some layers of the atmosphere might be above the limit, while others are below it. The star can exist in a state where parts of it are stable and parts of it are actively being blown away at the same time. This is why hypergiants are such a headache for astrophysicists. The models that work for normal stars don't quite work here. You can't just plug in the mass and luminosity and predict what the star will do. You have to account for opacity effects, for clumpy atmospheres, for eruption-driven mass loss, for pulsations, for magnetic fields that might be channeling material away from the surface in specific directions. Every hypergiant is a special case. Every one requires a custom model. And even then, the models don't always match the observations. Rho Cassiopei's 2000 outburst was not predicted. Nobody saw it coming. The star was being monitored, but the eruption happened faster than anyone expected. By the time astronomers realized what was happening, the outburst was already underway. The data collected during and after the event has been invaluable. It's given us a detailed look at what happens when a hypergiant loses control, but it's also raised more questions than it answered. Why did the outburst happen when it did? What triggered it? Will it happen again on a predictable schedule, or is the timing random? We don't know. The best we can do is keep watching and hope we're looking in the right direction when the next one erupts. Mass loss in hypergiants isn't optional, it's existential. These stars are so luminous that they cannot hold onto their outer layers indefinitely. Radiation pressure is constantly pushing outward. Gravity is barely strong enough to resist. The balance is so delicate that even minor fluctuations in the interior can tip the scales. a surge of energy from shell burning, a change in the opacity of a particular layer, a pulsation that amplifies into a full-blown eruption. Any of those can trigger mass loss, and once the mass loss starts, it feeds itself. The star gets smaller. The luminosity might drop slightly, but the surface gravity drops more. Lower surface gravity means weaker binding. Weaker binding means more mass loss. The star sheds layers like an onion being peeled, each layer revealing a slightly denser, slightly hotter interior underneath. Eventually, the star will lose so much mass that it drops out of the hypergiant category entirely. It will contract, heat up, and possibly transition into a different kind of object. A Wolf-Rayet star, a bare stellar core stripped of its hydrogen envelope and fusing helium or heavier elements directly at the surface, or it will run out of fuel entirely, collapse and explode. Either way, the hypergiant phase doesn't last. It's a brief window in the star's life where it's simultaneously at its largest and at its most unstable. The size is impressive, the instability is terrifying, and the fact that we can study these objects at all is a small miracle of timing. What you're seeing when you look at a hypergiant is a star that's falling apart in slow motion, not exploding, not collapsing, just bleeding, shedding mass, ejecting shells of plasma into space, pulsing like a cosmic heart that's about to give out. The surface is a battlefield where radiation pressure and gravity are locked in a fight that gravity is slowly losing, and the star knows it. If a star could know anything, it's losing mass it can't afford to lose. It's burning fuel it doesn't have. It's holding itself together with rules that barely apply anymore. And in a few 100,000 years, maybe less, it will be gone. Exploded, collapsed, transformed into something smaller and denser and quieter. The hypergiant phase will be over. The bleeding will stop. And what's left will be either a black hole, a neutron star, or a cloud of expanding debris enriched with every element the star managed to forge before it died. But for now, the star is still there, still bleeding, still pulsing, still defying the limits that should have torn it apart 1,000,000 years ago. And the reason it can defy those limits, the reason it exists at all, is because the limits aren't as hard as we thought. The Eddington limit is a guideline, not a law. Stars can exceed it temporarily. They can oscillate around it. They can exist in states that our models say shouldn't be stable, but somehow are, at least for a while. Hypergiants are proof that the universe has more tricks than we've accounted for, that stars can be bigger, stranger, more violent than the equations predicted, and that sometimes the only way to learn what's possible is to watch something impossible actually happen. Here's the problem. We've been mapping the Milky Way's population of massive stars for decades. We've catalogued thousands of blue supergiants, hundreds of red supergiants, dozens of hypergiants. We've measured their masses, their luminosities, their surface temperatures. We've watched them pulse, watched them eject shells of gas, watched them dim and brighten on timescales short enough that a single human astronomer can track their changes over a career. And when you take all that data and compare it to what our models of stellar evolution predict should be out there, the numbers don't match. Not close, not even in the right ballpark. There are too many hypergiants, or maybe not enough of something else. The discrepancy depends on how you frame it, but either way, the models and the observations are telling different stories, and after more than 50 years of trying to reconcile them, we're still not entirely sure why. The basic problem is this. Stellar evolution models start with a cloud of gas. You plug in an initial mass, say 40 solar masses. You set the chemical composition, mostly hydrogen and helium, with a dash of heavier elements. You let the equations run. Gravity pulls the cloud inward, temperature rises, fusion ignites. The star settles onto the main sequence and starts burning hydrogen. The model tracks what happens next. How long the star spends on the main sequence, how it evolves when the core hydrogen runs out, whether it becomes a blue supergiant, a yellow supergiant, a red supergiant, how much mass it loses through stellar winds, how long each phase lasts, when and how it dies. The models are sophisticated. They account for energy transport, opacity, convection, rotation, magnetic fields, mass loss. They've been refined over decades. They work. They predict the properties of normal stars with impressive accuracy. But when you use those same models to predict how many hypergiants should exist in a galaxy like the Milky Way at any given moment, the answer you get is smaller than the number we actually observe, by a lot. The models say hypergiants should be extraordinarily rare because the phase is so short. A star only spends a few thousand years as a red hypergiant before either collapsing or exploding. That's a blink. If you take the birth rate of massive stars in the galaxy, run them all through the evolutionary models, and count how many should be in the hypergiant phase right now, you get maybe a handful, a few dozen at most. We've found more than that, significantly more. And the ones we've found are probably only a fraction of the total because most of the galaxy is hidden behind dust and distance. The discrepancy is uncomfortable. Flip the problem around and it gets worse. The models predict that there should be a large population of very massive stars, stars with 50, 60, 80 solar masses still on the main sequence or just beginning to evolve off it. Blue supergiants. Hot, compact, luminous. These stars should be common because they spend a few million years in that phase, which is long enough that at any given moment there should be thousands of them scattered across the galaxy. We don't see thousands, we see hundreds, maybe. The very massive stars that the models say should dominate the upper end of the mass spectrum are missing, or at least underrepresented, and sitting in their place are hypergiants. Stars that have already evolved off the main sequence, already swollen to enormous size, already losing mass at catastrophic rates. Stars that should be rare but aren't. This is what astronomers call the massive star problem. It's not one problem, it's a whole tangle of them. Missing blue supergiants, too many red supergiants, hypergiants that exist when they shouldn't, or at least not in the numbers we observe. The models aren't completely wrong. They get a lot of things right. But somewhere in the gap between theory and observation, something is happening that we haven't fully accounted for, and the leading suspects are all processes that complicate the tidy picture of a star evolving in isolation. Start with the simplest explanation. Maybe stars don't evolve in isolation. Maybe most massive stars are born in binary systems. Two stars orbiting a common center of mass, close enough that they interact. Close enough that one star's gravity can pull material off the other. Close enough that as they evolve, they can exchange mass, merge, or tear each other apart. Binary interactions are messy. They throw off the neat evolutionary tracks that single-star models predict, and they're common. Surveys suggest that more than half of all massive stars are in binary systems. Some estimates push that fraction even higher. If binary evolution is the norm and single-star evolution is the exception, then our models have been trying to explain a population using a framework that only applies to a minority of cases. Here's what happens when two massive stars orbit close together. The more massive star evolves faster. It exhausts its core hydrogen first and starts to expand into a red supergiant. As it swells, its outer layers reach toward the companion star. Eventually, the expanding envelope crosses a boundary called the Roche lobe, the region around each star where its gravity dominates. Once the envelope crosses that boundary, the companion's gravity starts pulling material away. Gas streams from the bloated supergiant onto the smaller, hotter companion. The supergiant loses mass, the companion gains it. The supergiant, now lighter, contracts slightly and might avoid becoming a full hypergiant. The companion, now heavier, becomes overluminous for its age. It looks like a massive main sequence star, but it's actually a mass gainer. Its evolution has been altered by the infall of material it didn't start with. This process is called mass transfer, and it can produce stars that look nothing like what single-star models predict. A star that was born with 20 solar masses and gained another 10 from a companion will behave differently from a star that was born with 30 solar masses. The internal structure is different. The rotation rate is different. The chemical composition of the outer layers might be different if the transferred material came from a companion that had already started fusing heavier elements. Mass transfer can create blue supergiants that are too massive for their age, red supergiants that are too light, and hypergiants that shouldn't exist yet but do because their evolution was accelerated by interaction with a companion. Now take it a step further. What if the two stars don't just exchange mass? What if they merge? If the binary orbit is tight enough and the stars lose orbital energy through tidal interactions or mass loss, they can spiral inward. Eventually, they collide. The merger is violent. The two cores smash together. The envelopes mix. What you're left with is a single star with a combined mass, a scrambled internal structure, and an evolutionary history that no single star model can reproduce. Merger products can look like almost anything. A blue supergiant with an oddly high rotation rate and a surface composition that doesn't match its luminosity. A red hypergiant that formed too quickly. A yellow hypergiant in a phase that should only last a few hundred years, but somehow the star is there anyway, glowing brightly, refusing to follow the script. Mergers solve a lot of problems. They explain why we see hypergiants that look too young. They explain why some massive stars have chemical abundances that don't match standard evolutionary tracks. They explain the missing massive stars. If a significant fraction of the massive star population is actually made up of merger products, then the single-star models were never going to predict the right population numbers because they were solving the wrong problem. The question isn't why hypergiants exist. The question is why we thought they should be rare when stellar mergers are common enough to populate the hypergiant phase with products that wouldn't exist otherwise. The evidence for this is starting to pile up. In the Large Magellanic Cloud, a small satellite galaxy orbiting the Milky Way, astronomers surveyed nearly 60 blue supergiants and measured their surface compositions. They found that a large fraction of those stars had abundance patterns consistent with being merger products. Too much nitrogen at the surface, not enough carbon. Ratios that suggested the stars had dredged up material from their cores or mixed in material from a companion that had already processed its hydrogen into heavier elements. When researchers ran merger simulations and compared the predicted surface chemistry to the observations, the match was good, better than the match you get from single-star models. The blue supergiants weren't evolving in isolation. They were the wreckage of collisions. Another clue comes from the binary fraction itself. If hypergiants are the products of binary evolution, you'd expect to find them in binary systems. But we don't, or at least not often. One survey of galactic hypergiants found only one confirmed binary system among 16 objects. That's a much lower binary fraction than you see in the general population of massive stars. So either hypergiants are weird outliers that formed in isolation, which seems unlikely given how common binaries are, or the hypergiants we're seeing are the result of mergers that have already happened. The companion is gone, absorbed into the primary star, and what we're looking at is the merger product sitting there alone, overluminous and oversized, a single star with the mass and evolutionary history of two. Now add rotation. Stars spin, most of them, and rotation changes everything. A rapidly rotating star is not spherical, it bulges at the equator. The centrifugal force counteracts gravity, reducing the effective surface gravity at the equator and making it easier for material to be flung off. Rotation also drives internal mixing. In a non-rotating star, the core and the envelope are relatively isolated. Material in the core undergoes fusion, creates heavier elements, and those elements mostly stay in the core. In a rapidly rotating star, the rotation stirs the interior. Fresh hydrogen from the envelope gets mixed down into the core. Helium and heavier elements from the core get mixed up into the envelope. The star becomes chemically homogeneous. The boundary between core and envelope blurs. This process is called rotational mixing, and it drastically alters a star's evolution. A rapidly rotating massive star can stay on the main sequence longer because mixing replenishes the core with fresh hydrogen fuel. When it finally does evolve off the main sequence, it might skip the red supergiant phase entirely and go straight to a Wolf Rayet star, a stripped core burning helium at the surface. Or it might become a blue hypergiant, a rare intermediate phase where the star is overluminous and unstable but hasn't yet swollen into a red giant. The exact path depends on the initial rotation rate, the mass, and the metallicity. Stars born with more heavy elements lose mass more efficiently through stellar winds, which carry away angular momentum and slow the star down. Stars born in low metallicity environments keep their angular momentum longer and can rotate fast enough to drive homogeneous evolution. This brings us to metallicity, which is astronomer speak for how much stuff heavier than helium a star contains. The term is misleading because it includes elements like carbon, nitrogen, and oxygen, which are not metals in the chemical sense. But the terminology is baked in at this point, so we're stuck with it. Metallicity matters enormously for massive stars. High metallicity means more opacity in the outer layers. More opacity means radiation gets trapped more easily. Trapped radiation drives stronger stellar winds. Stronger winds strip away the outer envelope faster. A high metallicity massive star loses mass quickly, which reduces its luminosity and can prevent it from ever reaching the hypergiant phase. It sheds its hydrogen envelope, exposes its core, and becomes a Wolf Rayet star long before it has a chance to swell up. Low metallicity stars lose mass much more slowly. The winds are weaker because there are fewer heavy elements to absorb the outgoing radiation. Without strong winds, the star holds onto its envelope longer. It stays massive, it stays luminous, and when it finally does evolve off the main sequence, it can swell to enormous size because there's still a thick hydrogen envelope to inflate. This is why hypergiants are more common in low metallicity environments like the Magellanic Clouds. The stars there were born with fewer heavy elements. Their winds are gentler, they evolve differently, and they're more likely to pass through a hypergiant phase before exploding. There's even a proposed critical metallicity threshold. One set of models found that around a metallicity of 0.1% of the Sun's metallicity, roughly 1,000th, the behavior of massive stars changes sharply. Above that threshold, winds are strong enough to strip the envelope, and most massive stars end their lives as blue or yellow supergiants. Below that threshold, winds are too weak to strip the envelope, and the stars swell into cool red supergiants and hypergiants. The transition isn't gradual. It's a cliff. Cross the threshold and the population flips. The models predict that in the early universe, where metallicity was much lower than today, hypergiants should have been common. The first generations of massive stars would have swollen to sizes we can barely measure, lost mass through gentle winds instead of violent stripping, and eventually collapsed into black holes without ever exploding. We can test this, sort of. The Magellanic Clouds have lower metallicity than the Milky Way. Observations show that red supergiants are more common in the clouds relative to blue supergiants than they are in the Milky Way. The numbers shift exactly the way the models predict. Lower metallicity, more red supergiants. Higher metallicity, more blue supergiants and Wolf-Rayet stars. The metallicity hypothesis works, which means that any model trying to explain hypergiants has to account for where the star was born and what it was made of. A star born in the Milky Way evolves differently from the same mass star born in the small Magellanic Cloud, and neither of them evolves the way a star born in the early universe would have. Now put all three factors together: binary interactions, mergers, rotation, metallicity. Every one of them changes the story. A massive star born in a low metallicity environment with a close binary companion and a high initial rotation rate will follow an evolutionary path that looks nothing like the path a single non-rotating solar metallicity star would follow. And the problem is that we don't know ahead of time which combination applies to any given star. We can measure the current mass and luminosity. We can estimate the metallicity from the spectrum. We can sometimes detect a companion if the binary is wide enough and bright enough. But we can't rewind the clock and see what the star looked like 10 million years ago. We can't measure its birth rotation rate or whether it merged with a companion early in its life. We're trying to reconstruct a biography from a single snapshot, and the snapshot doesn't tell us which path the star took to get there. This is why the field is still refining the models. Every few years, a new paper comes out with updated prescriptions for mass loss or rotation or binary mass transfer. The models get more sophisticated. They include more physics. And with each update, the predicted populations shift slightly closer to what we actually observe. But we're not there yet. The tension hasn't been fully resolved. Some surveys still find more hypergiants than the models predict. Some find fewer massive main sequence stars. The distribution of stars in luminosity and temperature space, what astronomers call the Hertzsprung-Russell diagram, doesn't quite match the distribution the models produce. One recent study argued that mergers have to be common, not occasional, not rare, common. The researchers ran population synthesis models that tracked thousands of massive stars through their lives, including binary interactions and mergers. They found that to reproduce the observed distribution of blue supergiants and hypergiants, you need mergers to account for a significant fraction of the population, maybe 20%, maybe more. Without mergers, the models underproduce blue supergiants. With mergers, the numbers line up. The implication is that a huge chunk of the massive stars we see in the sky are not single stars evolving in isolation. They're the products of collisions, gravitational train wrecks that happened millions of years ago and left behind objects that look like normal stars but have evolutionary histories that are anything but. There's a subtle point here that's easy to miss. When we talk about stars that shouldn't exist, we're not saying they violate the laws of physics. We're saying they don't fit the simplified models we built based on assumptions that turned out to be wrong. Single-star evolution is clean, it's predictable, it's easy to model, but it's not what most stars do. Most massive stars are born in clusters with hundreds of siblings. They interact. They steal each other's gas. They merge. They get spun up by tidal forces. And every interaction nudges them off the tidy evolutionary track that the models predict. The models aren't useless, they're just incomplete. They describe a universe where stars evolve alone, and that's not the universe we live in. So why do hypergiants exist when the models say they shouldn't? Because the models were asking the wrong question. They were trying to predict the population of massive stars, assuming those stars evolved in isolation, with no companions, no mergers, no unusual rotation. And under those assumptions, hypergiants are rare. But massive stars don't evolve in isolation. They're born in binaries. They merge. They spin. They live in environments with different metallicities that change how fast they lose mass. And when you account for all of that, hypergiants stop being anomalies. They become expected. Not common, but expected. The products of processes that happen often enough that at any given moment there are dozens of them scattered across the galaxy. The observational side is catching up. New surveys are measuring the binary fractions of massive stars in different environments. Spectroscopy is getting good enough to detect subtle chemical signatures that reveal whether a star is a merger product or a mass gainer. Interferometry is resolving the surfaces of nearby hypergiants and tracking how they pulsate and eject material. Every new dataset refines the picture, and every refinement points in the same direction. Massive star evolution is not a solo act. It's a messy, chaotic, interactive process where the stars we see today are shaped as much by what happened to them as by what they were born with. There's one more twist. Some of the hypergiants we observe might not even be on their way to becoming supernovae. If a star loses enough mass through winds and eruptions, its core might never get hot enough or dense enough to ignite the final stages of fusion. The star just sheds layers until the core is exposed, cools down and fades. No explosion, no supernova. Just a quiet collapse into a black hole, hidden behind the debris of its own mass loss. We call these events failed supernovae, and we've detected hints of them. Stars that were there one year, dimmed dramatically, and then disappeared without the bright flash you'd expect from a supernova. If hypergiants can fail to explode, then the entire endpoint of massive star evolution is messier than we thought. Some stars go out with a bang, others just fade. The irony is that hypergiants exist because stars are more complicated than we gave them credit for. For decades, the standard model of stellar evolution treated stars as isolated spheres burning fuel in neat, predictable stages. And that model worked well enough for most stars that we kept using it. But when you push to the most massive objects, the ones burning fuel the fastest and living the shortest lives, the simplifications break down. Binaries matter, mergers matter, rotation matters, metallicity matters. And once you include all of those factors, the population you predict starts to look a lot more like the population you observe. Hypergiants aren't cosmic accidents. They're the inevitable result of massive star evolution playing out in a universe where stars don't evolve alone, where collisions and interactions and environmental differences produce outcomes the simplified models never anticipated. So the answer to why hypergiants exist when they shouldn't is that they should. We just didn't realize it until we looked closely enough at what was actually out there and asked why the numbers didn't match. The models are getting better, the observations are piling up, and the picture that's emerging is one where hypergiants are rare, unstable, short-lived, but entirely expected once you account for the full range of processes that shape how massive stars live and die. They're not breaking the rules, they're following rules we didn't know we'd forgotten to write down. And every hypergiant we find, every spectrum we take, every outburst we watch, adds another piece to the puzzle. The stars are teaching us what's possible. We just have to be willing to listen. We've been watching these stars bloat to sizes that barely make sense. We've measured their mass loss. We've tracked their pulsations. We've catalogued the ways they tear themselves apart while somehow staying intact. Now we need to talk about what happens when they finally lose that fight. When the fuel runs out, when the core collapses, when a star that has been bleeding light for millions of years suddenly runs out of options and everything goes wrong at once. This is not a gentle process. This is not a fade to black. This is violence on a scale that makes every supernova you've ever heard about look like a firecracker. Hypergiants don't retire. They don't cool down and drift quietly into the cosmic background. They explode, or they collapse. Or, in the most extreme cases, they do both. And when they do, they leave behind objects so dense and so strange that calling them remnants almost feels inadequate. A neutron star is not the leftover ash of a dead fire. It's a ball of matter so compressed that a teaspoon of it would weigh as much as a mountain. A black hole is a region where space itself has been torn open and the rules stop applying. These are the endpoints, the final states, the things that remain after a star has spent everything it had and gravity finally wins. Let's start with the simplest case, if simple is even the right word. A massive star, somewhere between 8 and 20 solar masses, burns through its fuel in stages. Hydrogen fuses into helium, helium fuses into carbon and oxygen, carbon fuses into neon and magnesium, oxygen fuses into silicon, silicon fuses into iron. Each stage happens faster than the last because each stage releases less energy. Hydrogen fusion can run for millions of years. Helium fusion lasts a few 100,000. Carbon burning might take a few centuries. Silicon burning lasts about a day, one day. The star spends millions of years building up to silicon fusion and then burns through it in 24 hours. And when the silicon is gone, there's nothing left to burn. Iron doesn't fuse. Fusing iron consumes energy instead of releasing it. The moment the core turns to iron, the clock stops. The core has no way to generate outward pressure. Gravity has been waiting for this moment, and gravity does not hesitate. The core collapses, not slowly, not over years or even minutes. The collapse happens in less than a second. A core the size of Earth compresses down to something the size of a city, 20 kilometers across. The density skyrockets. Electrons get crushed into protons, forming neutrons and releasing neutrinos. The neutrinos, which normally pass through matter as if it weren't there, suddenly find themselves trapped in a core so dense that even they can't escape immediately. The pressure builds, and then the core rebounds. The infalling outer layers slam into the now rigid neutron core and bounce. The bounce sends a shock wave racing outward through the star's envelope. The shock wave tears through layers of silicon, oxygen, carbon, helium, and hydrogen, heating them to billions of degrees. The star explodes. Everything outside the core gets blown into space at speeds approaching 10% the speed of light. What you see from Earth, if you happen to be looking in the right direction, is a supernova. A point of light that wasn't there yesterday, suddenly blazing bright enough to outshine an entire galaxy. A supernova is one of the most luminous events in the universe. For a few weeks, a single exploding star can radiate more energy than 100 billion normal stars combined. The explosion is visible across millions of light years. If Betelgeuse exploded tomorrow, it would be bright enough to cast shadows at night. You could read a book by the light of a dying star 650 light years away. The last time a supernova was visible to the naked eye in our galaxy was in 1604. Kepler saw it. It was called Kepler's star, a name that stuck even though Kepler didn't make it explode, he just wrote about it. Before that, Tycho Brahe observed one in 1572. Before that, Chinese astronomers recorded several over the past 2,000 years. Each one was treated as an omen, a new star appearing where there had been none. They didn't know they were watching something die. They thought they were watching something being born. The explosion does more than just light up the sky. It scatters the star's guts across light years of space. Every element heavier than hydrogen that the star managed to fuse during its life gets ejected. Carbon, nitrogen, oxygen, silicon, iron, gold, uranium. All of it forged in the core or created in the final seconds of the explosion itself, blown outward in an expanding shell of hot gas and dust. That shell will keep expanding for thousands of years, eventually mixing with the surrounding interstellar medium, and when the next generation of stars forms, they'll be built from material that includes the ashes of the previous generation. This is how the universe got complicated. The first stars were made of pure hydrogen and helium. They fused heavier elements, exploded, and seeded the gas clouds with carbon and oxygen. The second generation of stars incorporated those elements. They fused even heavier elements, exploded, and added more to the mix. Every generation builds on the wreckage of the last. The iron in your blood was forged in a supernova. The calcium in your bones came from a dying star. You are built from stellar debris. That's not poetic exaggeration, that's geology. Now step it up. A hypergiant with 30 or 40 or 50 solar masses doesn't follow the same script. It burns faster. It fuses heavier elements. It builds up a more massive core. And when that core collapses, the rebound might not be enough. The shockwave might stall. The outer layers might fall back onto the core instead of being blown away. If enough material falls back, the core can't hold. Neutron degeneracy pressure, the quantum mechanical force that stops a neutron star from collapsing further, has a limit. If the core exceeds about 2 to 3 solar masses, degeneracy pressure fails. Nothing can stop the collapse. The core keeps falling inward. Space curves around it. The curvature becomes so extreme that light can no longer escape. An event horizon forms. The core has become a black hole, and the outer layers, instead of being blown into space, fall into the black hole and disappear. This is called a failed supernova, though the name undersells what's actually happening. The star doesn't fail to explode. It starts to explode, and then the explosion fails. The shock wave stalls. The outer layers reverse direction and fall back in. From the outside, you see the star dim. Maybe it brightens slightly as the initial shock wave reaches the surface. Then it fades, and then it's gone. No bright explosion, no expanding nebula, just a star that was there and now isn't. Astronomers have caught this happening. In 2009, a yellow supergiant in a nearby galaxy called NGC 6946 was shining at a luminosity of about 1 million times the Sun. By 2015, it had faded by more than 98%. Follow-up observations with the Hubble Space Telescope and the Spitzer Space Telescope found weak infrared emission at the star's location, consistent with a faint remnant surrounded by dust. The star didn't explode, it imploded. Quietly. And what's left is probably a black hole sitting where a supergiant used to be. Failed supernovae are harder to detect than successful ones because there's no bright flash to catch your attention. You have to be monitoring the star before it collapses. You have to notice when it dims. And you have to follow up quickly enough to confirm that it didn't just get obscured by a dust cloud or eject a shell that temporarily blocked the light. Most of the time, we don't catch them. The star disappears, and we only realize it's gone years later when someone goes back through archival images and notices that a bright source is missing. Current estimates suggest that somewhere between 10 and 30% of massive stars might end as failed supernovae. If that's accurate, it means a significant fraction of black holes form without any fireworks at all. The universe's most extreme objects appearing not with a bang, but with a whimper. But when a massive star does explode successfully, and when the core collapses all the way to a black hole, you don't get a normal supernova. You get something worse, a hypernova. The term gets thrown around loosely, but the technical definition is an explosion with an energy output at least 10 times higher than a typical supernova. Where a normal supernova releases about 1 foe of energy, a foe being 10 to the 51st ergs, a completely made-up unit that exists only because astronomers got tired of writing out all the zeros. A hypernova releases 10 foe or more. That's 10 to the 52nd ergs. The number is so large, it stops meaning anything unless you drag it into context. A single hypernova releases as much energy in a few seconds as the Sun will produce over its entire 10 billion year lifetime. Multiply that by 1,000 and you're getting close. Hypernovae are rare. We've only confirmed a handful. They happen when a very massive star, probably something with an initial mass above 40 solar masses, collapses and forms a rapidly rotating black hole. As the black hole forms, material from the collapsing core swirls around it in an accretion disk. The material heats up. It gets compressed. Magnetic fields anchored in the disk get twisted and amplified, and then something extraordinary happens. The magnetic fields channel a fraction of the infalling material into 2 narrow jets shooting out along the black hole's rotation axis. The jets punch through the collapsing star, drilling holes through thousands of kilometers of gas in seconds. When the jets break through the surface, they release a burst of gamma rays, the most energetic form of light, the kind of radiation that can sterilize planets. This is a gamma ray burst, a GRB. For a few seconds to a few minutes, a collapsing star becomes the brightest object in the universe. Not the brightest star, the brightest object, more luminous than every other star and galaxy in the observable universe combined. If you could somehow see in gamma rays and you were looking at the right patch of sky at the right moment, a GRB would outshine everything. The entire rest of the cosmos would fade into the background. One dying star, billions of light years away, briefly dominating the sky. GRBs come in 2 varieties. Long-duration bursts, lasting more than 2 seconds, are associated with the collapse of massive stars. Short-duration bursts, lasting less than 2 seconds, are now known to come from the merger of 2 neutron stars, or a neutron star and a black hole. The distinction matters because the 2 types tell different stories. Long GRBs are the death cries of hypergiants. Short GRBs are the collisions of remnants left behind by earlier supernovae. Both produce jets, both release gamma rays, both are catastrophically energetic. A short GRB lasting less than 2 seconds can unleash as much energy as the Sun will produce in 10 billion years. That number was not a typo. Less than 2 seconds, the entire lifetime energy output of a star, gone in the time it takes you to blink. The jets are the key. Without jets, the energy from the collapse would radiate more or less evenly in all directions. It would still be bright, but the energy would be spread over the entire sky, diluted by geometry. With jets, all that energy gets focused into 2 narrow beams. If you're unlucky enough to be in the path of one of those beams, you see a GRB. If you're off to the side, you see a much fainter explosion, or possibly nothing at all. This is why GRBs are so bright. It's not that they're producing more total energy than a supernova. They are, but not by the factors you'd expect based on the brightness. What makes them so luminous is that they're beaming the energy toward you instead of spraying it in every direction. The jet acts like a spotlight. If the spotlight is aimed at your face, it's blinding. If it's aimed at the wall, you barely notice it. GRBs were discovered by accident in the 1960s by military satellites designed to detect nuclear tests. The satellites picked up gamma-ray flashes coming from space. At first, nobody knew what they were. The data was classified. When it was finally published in 1973, astronomers realized they'd found a new class of cosmic explosion. It took another 2 decades to figure out where they were coming from. The breakthrough came when the Compton Gamma Ray Observatory and the Beppo-Sachs satellite pinned down the locations of GRBs precisely enough to identify their host galaxies. The galaxies were distant, billions of light-years away. That meant the bursts were enormously energetic. Only the collapse of massive stars or the merger of compact objects could produce that much power in such a short time. The connection to hypernova was cemented in 1998 when astronomers observed a GRB and then, a few weeks later, detected a supernova at the same location. The supernova was unusually bright and unusually energetic. It fit the profile of a hypernova. The timing was perfect. The GRB came first, marking the moment the core collapsed and the jets broke through. The supernova came later, when the shockwave from the explosion reached the outer layers of the star and blew them apart. The two events were linked. The GRB was the birth cry of a black hole. The supernova was the star's outer envelope catching up with the news that the core was gone. Since then, astronomers have found more examples, not many. GRBs are rare and hypernovae are rarer. You need a very massive star. You need it to collapse in a specific way, forming a black hole instead of a neutron star. You need the black hole to be rotating rapidly. You need the jets to align with your line of sight. Miss any one of those conditions and you either don't get a hypernova or you don't see it. The GRBs we detect are the ones where everything lined up. For every GRB we see, there are probably dozens of hypernovae exploding off-axis, their jets pointed away from Earth, invisible to our gamma-ray telescopes. The universe is more violent than it looks. Now here's the uncomfortable part. If a GRB happened in our galaxy, aimed at Earth, we'd be in trouble. Gamma rays don't penetrate the atmosphere, which is good because it means we're shielded. But gamma rays hitting the upper atmosphere create secondary particles and radiation that can strip away the ozone layer. The ozone layer is what protects the surface from ultraviolet radiation. Lose the ozone and UV levels spike. DNA damage, mass extinctions, ecosystem collapse. There's speculation that one of Earth's past mass extinctions, the Ordovician extinction about 440 million years ago, might have been triggered by a nearby GRB. No proof. Just the observation that the timing lines up and the extinction pattern fits what you'd expect from a sudden increase in UV radiation. If it happened, the GRB would have been hundreds or thousands of light-years away, close by galactic standards. Distant enough that the star wouldn't have been remarkable to anyone looking up at the sky, just another faint point of light. And then one day, it exploded. The jet happened to be aimed in our direction, and every living thing on the surface that couldn't hide from ultraviolet light died. That's the thing about GRBs. They're not just bright, they're dangerous. Over cosmological distances, they're harmless. The inverse square law dilutes the energy. A GRB from 1 billion light-years away reaches Earth as a brief pulse of gamma rays that satellites detect, but that poses zero threat. But a GRB from within the galaxy, within a few thousand light-years, could be a civilization-ending event. The good news is that GRBs are rare in galaxies like the Milky Way. They require very massive stars, and very massive stars are rare. They also seem to favor low metallicity environments, regions where stars lose mass less efficiently and can grow large enough to become hypernova progenitors. The Milky Way's metallicity is relatively high. The star formation rate is relatively low compared to younger, more active galaxies. The odds of a nearby GRB happening in the next million years are small. Not zero, small. Let's talk about what's left after the explosion. If the core was between about 8 and 20 solar masses when it collapsed, and if the supernova succeeded in blowing away the outer layers, what remains is a neutron star, 20 kilometers across. A ball of neutrons so tightly packed that a cubic centimeter weighs as much as a mountain. The surface gravity is about 100 billion times stronger than Earth's. Drop something onto a neutron star from a height of 1 meter, and it hits the surface at roughly 1/3 the speed of light. The impact releases enough energy to vaporize whatever you dropped, and a chunk of the surface beneath it. Neutron stars are not places you visit. They're also not quiet. Many neutron stars spin rapidly. Some of them complete a full rotation in milliseconds. As they spin, they emit beams of radiation from their magnetic poles. If the magnetic axis is tilted relative to the rotation axis, the beams sweep across space like lighthouse beams. Every time the beam points at Earth, we detect a pulse. This is a pulsar. The first one was discovered in 1967 by Jocelyn Bell Burnell, a graduate student at Cambridge. She noticed a regular pulse in her radio data. The signal repeated every 33 seconds. It was so precise that she and her advisor briefly considered the possibility that it was a signal from an extraterrestrial civilization. They called it LGM-1, Little Green Men 1. It wasn't aliens. It was a neutron star, spinning, beaming, pulsing with the regularity of a cosmic clock. Pulsars slow down over time as they lose energy. The spin rate decreases. The pulses get farther apart. Eventually, after millions or billions of years, the pulsar spins down to the point where the beams are too weak to detect. The neutron star is still there, still spinning, just too faint to see. These are the dead pulsars, the remnants of remnants. Objects that have exhausted even the rotational energy left over from their violent birth. If the core is more massive, above about 3 solar masses, neutron degeneracy pressure can't hold. The collapse continues. The neutron star becomes a black hole. There's no explosion this time, no outward shock, just an implosion, a core collapsing past the point of no return. Space curves so sharply that a boundary forms, the event horizon, beyond which nothing can escape. Not matter, not light, not information. The black hole is invisible. You can't see it directly. You can only infer its presence by watching how it affects nearby matter. Gas falling toward the black hole heats up, glows, and emits X-rays. Stars orbiting the black hole move in ways that only make sense if there's a massive, invisible object at the center of their orbits. The black hole is there. You just can't look at it. Stellar mass black holes, the ones left behind by collapsing massive stars, weigh anywhere from a few solar masses to a few dozen. They're small by black hole standards. The supermassive black holes at the centers of galaxies weigh millions or billions of solar masses. Stellar black holes are the runts, but they're still black holes, still regions where the rules break. Still objects that will exist longer than stars, longer than galaxies, longer than anything else in the universe except maybe other black holes. When a massive star collapses and forms a black hole, it's creating something that will outlast everything. The star burned for a few million years. The black hole will persist for 10 to the 100 years or more, a number so large it has its own name, a Google, and even that might be an underestimate. Black holes evaporate through Hawking radiation, but the process is so slow that stellar mass black holes won't evaporate until long after the last star in the universe has burned out. Every supernova, every hypernova, every collapsing core leaves something behind. Neutron stars, black holes, expanding shells of gas enriched with heavy elements. The gas eventually cools, clumps together, and forms new stars. Those stars fuse more elements, die, and add more material to the mix. The cycle repeats. The universe recycles. Nothing is wasted. The calcium in your bones was fused in a dying star billions of years ago. It was ejected in a supernova, drifted through space for millions of years, condensed into a gas cloud, collapsed to form the sun and the planets, and eventually ended up in you. You're made of dead stars, literally. The atoms in your body have been through multiple stellar lifetimes. They've been fused, exploded, scattered, and reformed. And they'll be here long after you're gone, waiting for the next cycle. There's a concept that doesn't get talked about enough: light travel time. When you look at a distant star, you're not seeing it as it is now. You're seeing it as it was when the light left. Betelgeuse is 650 light-years away. The light reaching your eyes tonight left Betelgeuse in the year 1374. If Betelgeuse exploded yesterday, we wouldn't know for another 650 years. The explosion already happened. The shock wave is expanding. The core has collapsed into a neutron star or a black hole, but the light from the explosion hasn't reached us yet. It's still on its way, crossing the 650 light-years of space between the star and Earth at 300,000 kilometers per second. When it finally arrives, the star will have been gone for 6.5 centuries. We'll be seeing a supernova. We'll be watching something die, but the death already happened. We're just catching up to the news. Now scale that out. Stevenson 218 is 19,000 light-years away. The light you'd see tonight left that star 19,000 years ago. If the star exploded 18,000 years ago, we wouldn't know. The light from the explosion is still in transit. It won't arrive for another 1,000 years. The star could be gone. It could be a black hole by now. We're looking at a ghost, a light echo from something that no longer exists, and we won't know the truth until the light arrives. That's not unusual. That's normal. Every star in the night sky is a time machine. The farther the star, the further back in time you're seeing. Look at a star 1,000,000 light-years away and you're seeing what it looked like 1,000,000 years ago. It could be a supernova remnant by now. It could be a neutron star. You're seeing the past because light is fast, but space is large. This is what the phrase "dead stars whose light is only now reaching Earth" means. It's not poetic, it's literal. The star died, the light left. And now, thousands or millions of years later, the light is arriving. We're seeing the star as it was, not as it is. We're watching history, and the history is violent, because the stars that become hypergiants don't fade quietly. They don't dim slowly over billions of years. They explode or implode or collapse in events so energetic that they reshape the space around them. And when we see that explosion, when we detect that gamma-ray burst or that supernova, we're not seeing it happen. We're seeing it after it already happened. The delay is built into the speed of light. The universe is showing us its past, because the present is too far away to see. That gap, the space between when something happens and when we see it, is where the story lives. The hypergiants we observe might already be gone. The ones that will explode in our lifetime might not have been born yet. We're watching a slideshow, frame by frame, each frame delayed by the time it takes light to cross the distance between the star and the telescope. The universe is not happening in real time, it's happening in the past, and the farther you look, the deeper into the past you see. The stars we're watching die tonight, died thousands of years ago. The explosions we'll see tomorrow started before recorded human history, and the remnants, the neutron stars and black holes left behind, are out there right now, invisible, waiting for us to catch up. We've watched these stars swell to sizes that light takes 9 hours to cross. We've measured their mass loss, tracked their pulsations, mapped their violent deaths. We've talked about explosions that outshine galaxies and collapses that punch holes in space-time. But there's a detail we've been dancing around. A fundamental truth that changes everything about what we think we're seeing when we point a telescope at the sky. None of it is happening now. Not a single photon reaching your eye tonight is showing you the universe as it exists in this moment. You're looking at the past, always, without exception, and the further you look, the deeper into history you go. Light is fast, absurdly fast by any standard that matters to a human body. 300,000 kilometers per second, fast enough to circle the Earth 7.5 times in 1 second, fast enough to reach the moon in a bit over a second, fast enough that for most of your daily experience, the delay between something emitting light and you seeing it is so small it's irrelevant. The lamp across the room, the sun in the sky. Even the sun, which is 150 million kilometers away, only takes about 8 minutes for its light to reach Earth. 8 minutes is nothing. If the sun exploded right now, you'd have 8 minutes of normal daylight before the sky went dark. 8 minutes to finish your coffee. 8 minutes before the end of the world arrived at the speed of light. But space is not measured in rooms or even in solar systems. Space is measured in light years. The distance light travels in 1 year, about 9.5 trillion kilometers. And stars are not 8 light minutes away. They're light years away, decades, centuries, thousands of years. The nearest star to our solar system, Proxima Centauri, is about 4.2 light years away. The light you see from Proxima tonight left that star 4 years ago. If an astronomer on a planet orbiting Proxima Centauri aimed a telescope at Earth right now, they wouldn't see 2025. They'd see 2021. They'd be watching us deal with a pandemic. They'd be seeing our past because the light carrying that information is still in transit. It takes 4 years to cross the gap. There's no way around it. The speed of light is the speed limit of the universe. Information cannot travel faster. Causality itself is bound by that limit. Now scale it up. Betelgeuse is 650 light-years away. The light reaching Earth tonight left Betelgeuse in the year 1375. The star you're seeing is the star as it existed in the 14th century. If Betelgeuse exploded yesterday, we wouldn't know. The light from the explosion is still on its way. It's crossing the 650 light-years of empty space between the supergiant and Earth at 300,000 kilometers per second, and it won't arrive for another 650 years. By the time we see the explosion, it will be the year 2675. The supernova will have happened 7 centuries earlier. We'll be watching a recording. An ancient event finally catching up to us because the universe has a built-in delay, and Betelgeuse is close. Cosmically speaking, it's in our neighborhood. Stevenson 218 is 19,000 light-years away. 19,000. The light you'd see if you pointed a telescope at it tonight left that star 19,000 years ago. 19,000 years ago, humans were hunter-gatherers. We hadn't invented writing. We hadn't built cities. We were painting on cave walls and figuring out how to make fire reliably. That's how long ago the light left. The photons that hit the detector on a telescope today have been traveling through space since before the dawn of recorded history. And they're showing us a star that might not exist anymore. If Stevenson 218 exploded 18,000 years ago, we wouldn't know yet. The light from the explosion is still in transit. It won't arrive for another 1,000 years. The star could be a black hole by now, a neutron star, an expanding cloud of debris. We're looking at a ghost, a projection of what the star looked like 19 millennia ago, back when mammoths were still walking the Earth and the last ice age hadn't ended. The star you're seeing is not the star as it is, it's the star as it was, and the gap between those two states is unbridgeable. There is no way to see the present. The present is always too far away. This isn't a quirk of astronomy. This is how light works. This is how the universe works. Every star in the night sky is a time machine. The farther the star, the further back in time you're looking. Look at a star 100 light-years away and you're seeing what it looked like a century ago. 1,000 light-years, a millennium. 1,000,000 light-years, you're seeing the star as it existed 1,000,000 years ago, before humans existed, before hominids existed, back when our ancestors were still small mammals hiding from dinosaurs. No, wait, dinosaurs were gone by then. Back when our ancestors were hiding from whatever came after dinosaurs. The point is that looking at distant objects is looking at the past. There is no other option. The speed of light is finite. Space is large. The delay is mandatory. So when astronomers talk about observing distant hypergiants, they're not describing the stars as they are now. They're describing the stars as they were when the light left. And for objects 19,000 light-years away, that when is so far in the past that the entire span of recorded human history fits comfortably inside the gap. We are seeing ancient light. Light that has been traveling longer than civilization has existed. And we're using that light to infer properties of a star that might have already died, might have already exploded, might have already collapsed into a black hole. We won't know until the news arrives. And the news travels at the speed of light, no faster. This creates a strange situation. The universe you see when you look up at the night sky is not a snapshot of the present. It's a composite image of the past, with each star contributing light from a different moment in history. The nearest stars show you the recent past, a few years ago, a few decades. The distant stars show you the deep past, thousands or millions of years ago. The whole sky is a timeline, a layered record of events that happened at different times, all arriving at your eye in the same instant. You're not seeing the universe. You're seeing the universe's history, played back one photon at a time. Now let's talk about how astronomers measure the distances to these objects, because understanding the distance is the only way to understand the delay. For nearby stars, the method is straightforward: parallax. As Earth orbits the Sun, nearby stars appear to shift slightly against the background of more distant stars. The shift is tiny, measured in fractions of an arcsecond, but it's measurable. 1 arcsecond is 1/3600th of a degree. A parallax shift of 1 arcsecond corresponds to a distance of 1 parsec, which is about 3.26 light-years. The smaller the shift, the farther the star. Measure the shift, and you've measured the distance. Parallax works beautifully for stars within a few hundred light-years. Beyond that, the shifts get too small to measure accurately. even with space telescopes like Gaia, which has mapped the distances to more than 1 billion stars with unprecedented precision. For stars farther out, parallax doesn't work. The shifts are too small, so astronomers use other methods. One of the most reliable is the distance ladder, a series of overlapping techniques that build on each other. You start with parallax for nearby stars. Use those stars to calibrate the brightness of specific types of variable stars, like Cepheid variables, whose brightness fluctuates in a way that's directly tied to their true luminosity. Measure the period of the pulsation, and you know how luminous the star actually is. Compare that to how bright it looks from Earth, and you can calculate the distance. Cepheids are bright enough to be seen in nearby galaxies, so you can use them to measure distances out to millions of light years. Beyond Cepheids, you use supernovae, type 1 a supernovae specifically. These are exploding white dwarfs that all have roughly the same peak brightness. They're so bright that they can be seen across billions of light years. Spot a type 1 a supernova in a distant galaxy, measure how bright it looks, compare it to the standard brightness, and you get the distance. Each rung of the ladder extends the reach a little farther. Parallax gets you to a few hundred light years. Cepheids get you to a few million. Supernovae get you to billions. It's not perfect. Each step introduces uncertainties, but it works. And it's the best tool we have for mapping the scale of the universe. For hypergiants like Stephenson 218, the distance estimate comes from a combination of methods. The star is too far for parallax. It's not a Cepheid. It hasn't exploded yet. So astronomers look at the star's environment. What cluster is it in? What's the distance to that cluster? Are there other stars nearby whose distances are better constrained? They also look at the star's spectrum. The absorption lines tell you the surface temperature and the composition. From that, you can estimate the luminosity. Compare the estimated luminosity to the observed brightness, and you get a distance. The process is indirect. The uncertainties are large. Distance estimates for hypergiants can shift by thousands of light years depending on whose measurement you trust. But the range is narrow enough to be useful. Stephenson 218 is somewhere around 19,000 light years away. Maybe 18,000, maybe 20,000. The exact number matters less than the scale. It's far. Far enough that the light delay is measured in millennia. And then there's the dust. Because space is not empty, it's full of gas and dust, mostly hydrogen, some helium, trace amounts of heavier elements, and dust, tiny grains of carbon, silicates, ice. Each grain is microscopic. But there are trillions upon trillions of them scattered throughout the galaxy. And dust blocks light, visible light especially. Blue light gets scattered more than red light, which is why dust clouds look reddish and why stars behind dust appear dimmer and redder than they actually are. Astronomers call this extinction, not because the star is gone, because its light is being absorbed or scattered before it reaches the telescope. Extinction is a massive problem for studying hypergiants because hypergiants tend to live in regions with lots of dust. They're born in giant molecular clouds, dense regions of gas and dust where star formation is happening. And they're surrounded by dust they've ejected themselves through stellar winds and eruptions. When you point a telescope at a hypergiant, you're looking through layers of dust. The dust absorbs some of the light. It scatters some of it. It reddens the spectrum. The star looks fainter and cooler than it really is. If you don't correct for the dust, your distance estimate will be wrong. Your luminosity estimate will be wrong. Your size estimate will be wrong. Everything downstream of the observation gets skewed. Infrared observations help. Dust is more transparent to infrared light than to visible light. So, if you observe a hypergiant in the infrared, you can see through the dust and get a clearer view of the star underneath. This is why infrared telescopes like Spitzer and the James Webb Space Telescope are so valuable for studying obscured stars. They cut through the fog, but even in the infrared, dust matters. You still have to model how much dust is there, how thick it is, how much light it's blocking. The models involve assumptions. The assumptions introduce uncertainties, and the uncertainties propagate through every calculation you do afterward. The 2024 direct imaging of WOHG 64, a red supergiant in the Large Magellanic Cloud, is a perfect example of how dust complicates things. WOHG 64 is surrounded by a thick torus of dust, a donut-shaped cloud orbiting the star. Astronomers used interferometry to resolve the dust structure and measure its geometry. The observations revealed that the dust isn't uniform, it's clumpy, asymmetric. The star itself is off-center relative to the dust torus. That matters because if you're trying to estimate the star's size and you don't account for the dust geometry, you'll get the wrong answer. The dust can make the star look larger or smaller depending on how it's distributed. WOHG 64 was estimated at around 1,540 times the radius of the Sun in some analyses, but that number depends heavily on how you model the dust. Change the model and the size estimate changes. WOHG 64 is also notable because it's the first star outside the Milky Way to be directly imaged with interferometry, not photographed, imaged, resolved as a disk instead of a point of light. The Large Magellanic Cloud is about 160,000 light-years away. The light we're seeing left WOHG 64 160,000 years ago. That's before modern humans left Africa, before Neanderthals went extinct. The star we're imaging is a snapshot from the Pleistocene, and the imaging resolution is good enough that we can see structure in the dust around it. We can map the geometry of a cloud orbiting a star that's so far away its light has been traveling since before our species looked like it does now. This is where the cosmic timescale gets visceral. The stars we study are not contemporary objects, they're historical artifacts. Every observation is an archaeological dig. We're excavating the past using light as the primary evidence. And because the light has been traveling for so long, we're always working with old data. The star might have changed, it might have erupted, it might have died. We won't know until the updated light arrives. There's a built-in lag between reality and observation, and the lag is proportional to the distance. The farther the object, the older the information. Now imagine this. Right now, at this exact moment, there is a hypergiant somewhere in the galaxy collapsing. The core is running out of fuel. The outer layers are falling inward. The star is about to explode or implode. It's happening right now. But the star is 15,000 light-years away. We can't see it yet. The light from the collapse hasn't reached us. It's in transit. It's been in transit for thousands of years, and it will keep traveling for thousands more. 15,000 years from now, someone will point a telescope at that patch of sky and see a supernova, a bright new star where there was none before. And they'll be watching something that happened 15,000 years earlier. They'll be seeing the star die, but the death already happened in our present. They're just catching up. And here's the twist. There are stars that have already exploded, already collapsed, already disappeared, and we don't know it yet because the light from those events hasn't arrived. Somewhere out there in the galaxy, there's a hypergiant that blew itself apart 10,000 years ago. The supernova happened, the shock wave is expanding, the core has collapsed into a neutron star or a black hole. The remnant is glowing in X-rays, but we still see the star. we still see it shining, because the light from before the explosion is still arriving. The explosion light is behind it, working its way toward us, but it hasn't caught up yet. For us, the star is alive. In reality, it's been dead for 10 millennia. The truth is in transit, and it's traveling at the speed of light, no faster. This is not speculation, this is inevitable. Given the number of massive stars in the galaxy and the distances involved, there are statistically guaranteed to be stars that have already died, but whose death light hasn't reached us yet. We're looking at corpses and seeing them move. We're watching ghosts. And we won't know they're ghosts until the final photons arrive, carrying the news that the star is gone. There's a particular kind of loneliness in that realization. You're standing on a planet orbiting a star in a galaxy containing hundreds of billions of other stars, and you're surrounded by light from objects that might not exist anymore. The sky is full of phantoms, ancient light from ancient objects, some of which are still there and some of which have already moved on to whatever comes next. And you can't tell the difference. You can't separate the living from the dead. You can only watch the light and wait for updates that might not arrive in your lifetime. Astronomers are fond of saying that telescopes are time machines. That's not metaphor, that's mechanics. A telescope doesn't show you what's out there now. It shows you what was out there when the light left. Point a telescope at a galaxy a million light years away, and you're seeing that galaxy as it existed a million years ago. Point it at a galaxy a billion light years away, and you're seeing the galaxy as it was a billion years ago, back when Earth was still a ball of molten rock. The deeper you look into space, the further back in time you see. And the universe is big enough that we can see all the way back to the cosmic microwave background, the afterglow of the Big Bang itself, light that has been traveling for over 13 billion years. That light left when the universe was only 380,000 years old. It's been in transit ever since. And when it finally hits a detector on a satellite orbiting Earth, we're seeing the universe as it was at the very beginning. Infant light from an infant cosmos. The entire field of cosmology is built on this principle. We can't visit the early universe. We can't send a probe backward in time. But we don't have to. The early universe is still visible. Its light is still arriving. We just have to look far enough away, and there it is. The Big Bang isn't something that happened and ended. It's something that's still happening, in the sense that the light from it is still reaching us. The event is over. The evidence is ongoing. Hypergiants are the same. They're time capsules. Frozen moments from whenever the light left, projected forward across thousands of years of empty space, arriving at a telescope on a planet that didn't exist when the light began its journey. And every photon carries information, temperature, composition, motion. The star is talking to us, but it's talking from the past. The message is old, and by the time we decode it, the star might have moved on. It might have changed, it might be gone. This is the gap we can't close, the observational horizon, the boundary between what we can see and what's actually happening. Light is the fastest messenger the universe has, and even light takes time, centuries, millennia, eons. The universe is unfolding in real time, but real time is invisible. All we can see is history, layer upon layer of it, stacked across every distance scale, every wavelength, every object bright enough to send us a signal. The stars are distant, the light is old, and the present is always just out of reach. The hypergiants we study are not contemporary with us, they're relics. Light echoes from an era when human civilization didn't exist, when the pyramids hadn't been built, when the last ice age was still ending, and yet we measure them, we catalogue them, we estimate their sizes, their masses, their temperatures. We track their pulsations and their eruptions. We model their evolution and predict their deaths. All of it based on light that's been traveling for longer than history. All of it inherently backward-looking. We're astronomers. We study the past. The present is too far away to see, and somewhere out there, right now, a hypergiant is dying. The core is collapsing. The envelope is exploding. The star is ending, and we won't know for thousands of years. The light hasn't left yet, or it has, but it hasn't arrived. Either way, we're blind to it. Blind to the present, bound by the speed of light and the vastness of space to always be looking backward. The universe is a recorded history playing out in our telescopes, and the recording never stops. New light keeps arriving. Old events keep catching up. The past keeps unfolding into the present, one photon at a time, carrying news from stars that died before we were born and won't be confirmed dead until long after we're gone. That's the universe we live in, not a static photograph, a moving picture. A film reel stretched across space and time, where every frame is delayed by distance and every image is a memory of something that used to be. The stars are shining, but the light is old, and the story is still being written, somewhere out there in the dark, in a present we can't see and won't see until it becomes the past, and the light finally catches up. We've spent this entire video staring at objects so large they break our ability to visualize scale. Stars where light takes 9 hours to make a lap. Explosions that outshine galaxies. Remnants so dense that a teaspoon weighs as much as a mountain. And all of it, every measurement, every observation, every carefully constructed model, is based on light that left those objects thousands or millions of years ago and only just now arrived at a detector we built on a planet orbiting an average star in an unremarkable corner of a galaxy containing hundreds of billions of other stars. We are small. Our instruments are better than they used to be, but they are still limited, and the universe does not care. It keeps doing what it does, operating on timescales and distance scales so vast that the entire span of human existence, from the first stone tools to the James Webb Space Telescope, fits comfortably into a rounding error. Let's be very clear about what we can actually see. The observable universe has a radius of about 46.5 billion light-years, not 14 billion, 46.5. The confusion comes from the fact that the universe is roughly 13.8 billion years old, so you'd think the farthest thing we could see would be 13.8 billion light-years away. But space itself has been expanding the entire time the light was in transit. A photon that left a distant galaxy 13 billion years ago has been traveling toward us ever since. But the galaxy it came from has been moving away from us the whole time because the space between us and it is stretching. By the time the photon arrives, the galaxy is now 46 billion light-years away. The photon traveled 13 billion light-years through space that was actively expanding underneath it. It's like running on a treadmill that's also on a conveyor belt moving in the opposite direction. You run 13 miles, but you're now 46 miles from where you started because the ground kept moving while you were running. That 46.5 billion light-year radius defines the observable universe. Everything inside that sphere is, in principle, something we could see if we had a good enough telescope and enough time to point it in the right direction. Everything outside that sphere is invisible, not because it isn't there, because the light from it hasn't reached us yet. And for the most distant regions beyond the observable universe, the light will never reach us. Space is expanding faster than light can cross it. Those regions are moving away from us at speeds exceeding the speed of light, which sounds like it violates relativity, but doesn't, because it's space itself that's expanding, not objects moving through space. The distinction matters. Relativity says nothing can move through space faster than light. It says nothing about space itself stretching. And space is stretching, everywhere, all the time. The farther away something is, the faster it's receding. Eventually, you hit a distance where the recession speed exceeds the speed of light. Beyond that point, light emitted toward us will never catch up. It's running on a treadmill that's moving backward faster than it can run forward. It will never arrive. That distance is the cosmic horizon. And it is an absolute observational limit, not a technological limit, an informational one. The light will never get here. There is no instrument that can see past it. The universe beyond the horizon exists, probably, but it is causally disconnected from us. It cannot affect us. We cannot affect it. It might as well be a different universe entirely. So when we talk about the observable universe, we are talking about a bubble, a sphere of space centered on Earth, or more accurately centered on wherever the observer happens to be, containing every object whose light has had time to reach us since the Big Bang. The bubble is large, incomprehensibly large, but it is finite, and it is surrounded by more universe. How much more, we don't know. The universe could be infinite. It could be finite, but much larger than the observable portion. It could wrap around on itself in ways that make the entire concept of size meaningless. We don't know. We can't know. The only part we can study is the part we can see. Everything else is speculation, inference, and math. The James Webb Space Telescope has pushed the edge of that bubble closer to the beginning than any instrument before it. In 2024, Webb confirmed a galaxy that existed only 280 million years after the Big Bang. 280 million sounds like a long time. It isn't. The universe is 13.8 billion years old. 280 million years is roughly 2% of that. Webb is seeing galaxies that formed when the universe was still an infant, and those galaxies are not supposed to look the way they do. They're too massive, too bright, too well formed. The models predicted that galaxies in the early universe should be small, dim, chaotic clumps of stars struggling to pull themselves together. Webb found massive structured galaxies shining brightly, as if they'd had billions of years to mature when they'd only had a few 100 million. The observations don't match the predictions. Again, that's becoming a theme, but even Webb has limits. It can see back to roughly 280 million years after the Big Bang. It cannot see earlier, not because the technology isn't good enough, because there's nothing to see. The universe before that point was opaque. For the first 380,000 years after the Big Bang, the universe was a hot, dense plasma. Electrons and protons were not yet bound into atoms. Photons couldn't travel more than a short distance before scattering off a free electron. Light couldn't propagate. The universe was a glowing fog. Then, about 380,000 years in, the universe cooled enough for electrons and protons to combine into neutral hydrogen. The fog cleared. Photons could finally travel freely. The universe became transparent. That moment is called recombination, and the light from it is what we detect as the cosmic microwave background. The CMB is the oldest light in the universe. It has been traveling toward us for over 13 billion years, stretched by the expansion of space from visible and ultraviolet wavelengths all the way into the microwave. It is the earliest thing we can see with electromagnetic radiation. Before recombination, the universe was dark to us. Not because nothing was happening, because light couldn't escape. We can infer what happened before recombination. We have models. We have the physics of the early universe worked out in extraordinary detail, but we cannot observe it directly. The light from that era doesn't exist. It was absorbed and scattered before it could propagate. Observationally, we are blind to the first 380,000 years. That's not a lot of time compared to the age of the universe, but it's the time when everything important happened. The Big Bang, inflation, the formation of the first atomic nuclei, all of it hidden behind an opaque wall we cannot see through. Cosmologists call it the surface of last scattering. It's the farthest back we can see with light. Beyond that, we need other tools, gravitational waves maybe. Neutrinos, if we can detect them. But light, the primary tool of astronomy for the past 400 years, hits a hard stop. So we are limited. Limited by the speed of light, limited by the expansion of space, limited by the opacity of the early universe, and limited by the instruments we have built. Webb is the most powerful telescope humanity has ever launched. It cost $10 billion and took decades to design and build. It sits 1.5 million kilometers from Earth, in a gravitationally stable orbit where it can stare at the same patch of sky for weeks without interruption. It is a miracle of engineering, and it can see back to 280 million years after the Big Bang. 2% of cosmic history. That's the edge of our reach, for now. There are plans for bigger telescopes, ground-based ones with mirrors 30 meters across, space-based ones that could dwarf Webb, interferometers that combine the light from multiple telescopes to create effective apertures the size of continents. Every generation of instruments pushes the boundary a little farther. Every new dataset reveals objects we didn't think existed and forces us to revise the models, but the boundary is still there. We are still looking at a finite bubble, and the bubble is surrounded by the unknown. Let's bring it back to hypergiants, because the same limitations apply. Stephenson 218 is 19,000 light-years away. That's close by cosmic standards. It's in our own galaxy. And yet measuring its size requires assumptions, indirect methods, and models that are constantly being revised. We don't have a photograph of Stephenson 218. We have a point of light and a spectrum. From that, we infer temperature, luminosity, and size. The uncertainties are large. Different teams get different numbers. The star could be 2,000 solar radii. It could be 2,500. The error bars overlap, and the star itself is variable. It pulsates, it swells and contracts. Its size changes over time. Asking what the radius is assumes there's a stable answer. There isn't. The star is not a fixed object, it's a dynamic process. And we're watching it from 19,000 light-years away through layers of interstellar dust, using instruments that were not designed with this specific measurement in mind. Now consider that we've only surveyed a fraction of the galaxy. Most of it is hidden behind dust clouds or located on the far side, tens of thousands of light-years away, where distance and extinction make faint objects nearly impossible to detect. There could be hypergiants out there larger than Stephenson 218. We wouldn't know. They could be sitting in a molecular cloud, surrounded by so much dust that even infrared observations can't penetrate. They could be on the far side of the galactic core, blocked by the densest part of the Milky Way. They could have already exploded, and the light from the explosion is still in transit, so we still see them shining as if nothing happened. Every few years, someone announces the discovery of a new candidate for the largest known star. UY Scuti held the title for a while, then Stephenson 218. In 2024, astronomers using interferometry imaged WOHG 64 in the Large Magellanic Cloud and measured its radius at around 1,540 solar radii, give or take 77. Some papers argue WOHG 64 is the largest. Others argue for Stephenson 218. Others point to stars we haven't confirmed yet because the data is still being analyzed. The title keeps changing hands. Not because the stars are changing, though they are. Because the measurements are hard and the uncertainties are large, and every time someone builds a better instrument or refines the model, the numbers shift. And here's the uncomfortable part. Some of the earlier claims were wrong. Not lies, just wrong. Based on distance estimates that turned out to be too large, or models that didn't account for dust properly. When the errors were corrected, the stars shrank. Objects that were once listed as the largest known stars dropped down the rankings. The records are fragile. They depend on measurements made at the edge of our capabilities, and the edge of our capabilities is a noisy, uncertain place. This happens in astronomy more than people realize. A team announces a discovery. The media picks it up. The object gets a name and a place in the record books. Then another team takes a closer look and finds a problem. The distance was off. The luminosity was miscalculated. The size estimate assumed the wrong stellar model. The discovery gets revised, sometimes downward. Sometimes it disappears entirely. The object that was once the brightest, the largest, the most distant, turns out to be none of those things. It was a measurement error, a quirk of the data, a misidentification. Science corrects itself, but the corrections don't always make headlines. The initial claim does. The revision is a footnote. So the public memory is full of objects that are no longer believed to exist in the form they were originally reported. Hypergiants are particularly susceptible to this because they are rare, distant, and surrounded by complicating factors like dust and variability. Measuring them requires sophisticated models and assumptions that are hard to verify. When you're working at the edge of observability, mistakes are easy to make, and the stakes are low enough that they don't get the scrutiny of, say, a new particle discovery in physics. An astronomer publishes a paper claiming a star is 2,500 solar radii. Another astronomer redoes the analysis and gets 1,800. Both papers cite the same observations. They just used different models. Who's right? Maybe neither. Maybe both. The star is variable. The measurement is uncertain. The error bars are wide enough to accommodate multiple answers. This is normal. This is how science works when you're pushing the limits. But it means the record books are constantly being rewritten. So when we say Stephenson 218 is the largest known star, what we mean is that as of the most recent data we have, using the models we currently trust, and accounting for the uncertainties we're aware of, Stephenson 218 appears to be the largest. That statement could be wrong. It could be revised next year. It could be replaced by a new discovery next month. The universe is not handing us a sorted list. We are building the list ourselves, one difficult measurement at a time, and the list keeps changing as the data improves. Now pull back, way back. The Milky Way is one galaxy. There are an estimated 2 trillion galaxies in the observable universe. 2 trillion. Each one contains tens of billions to hundreds of billions of stars. Some contain more. The total number of stars in the observable universe is somewhere around 10 to the 24th. That's a 1 followed by 24 zeros. A trillion, maybe more. We have catalogued a few billion of them, maybe 10 billion if you count everything Gaia has measured. That's a tiny fraction, less than 1%. Most of the stars in the universe have never been observed individually. Most of them never will be. They're too faint, too far away, hidden behind dust or other stars, outside the reach of our instruments, and somewhere in that uncatalogued majority, there are hypergiants. Probably thousands of them, maybe tens of thousands. We've found a few dozen in the Milky Way. We've found a handful in nearby galaxies. The rest are out there, shining, pulsing, ejecting shells of plasma, ticking down toward explosions we will never see. Most of them will die without ever being noticed. No telescope will point at them, no spectrum will be taken, no distance will be measured. They will explode or collapse, leave behind a neutron star or a black hole, and the universe will move on. The only record of their existence will be the light they emitted, which is still traveling outward, spreading into the void, carrying information that no one will ever decode. That's the scale we're dealing with. A universe so large that even the most extreme objects, the biggest stars, the brightest explosions, the densest remnants are mostly invisible to us. We see a sample, a biased sample. The objects that happen to be close enough, bright enough, and positioned in a part of the sky we've bothered to survey. The rest is dark, not because it doesn't exist, because we haven't looked yet, or can't look, or won't look, because there are too many other things to look at and not enough time or money or telescope availability to cover everything. Astronomy is a game of triage. You can't study everything. You have to choose. Do you spend your telescope time mapping the nearby stars in exquisite detail, or do you push to the edge of the observable universe and study the first galaxies? Do you follow up on known hypergiants and track their variability, or do you search for new ones? Do you focus on objects in our galaxy where the measurements are easier, or do you look at other galaxies where the populations might be different? Every choice closes off other paths. Every observation is an opportunity cost. And the universe is bigger than the sum of all the observations humanity will ever make. We will never see it all. We will never catalog it all. We will always be working with incomplete data. And the universe, indifferent to our limitations, will keep doing what it does. The idea that the universe doesn't wait for us to understand it is not poetic, it's mechanical. Stars are forming right now in molecular clouds we can't see. They're evolving through phases we haven't modeled. They're exploding in galaxies too distant for the light to have reached us yet. Black holes are merging. Neutron stars are colliding. Hypergiants are ejecting shells of gas that will drift through space for millennia before colliding with other clouds and triggering new rounds of star formation. All of it is happening right now, at this exact moment. And none of it is waiting for a telescope to point in its direction. The universe does not pause for observation. It unfolds according to the laws of physics, blind to whether anyone is watching. This is humbling in a way that's hard to articulate. We have built instruments that can detect light from galaxies billions of light years away. We have measured the temperature of the cosmic microwave background to 5 decimal places. We have confirmed the existence of gravitational waves, ripples in space-time itself, produced by colliding black holes billions of years ago. We have landed robots on Mars, sent probes past the edge of the solar system, and mapped the surface of stars in other solar systems. The progress is real. The capabilities are extraordinary, and yet the unknown is still larger than the known, by orders of magnitude. We have surveyed a fraction of our own galaxy, a smaller fraction of nearby galaxies, a vanishingly small fraction of the observable universe, and the observable universe itself is a finite bubble surrounded by more universe that we can never see. There are entire populations of objects we haven't discovered yet, stars more massive than anything we've catalogued, black holes larger than anything we've measured, phenomena we don't have names for because we've never seen an example. The universe is not done surprising us. Every time we build a better telescope, we find something that doesn't fit the models. Galaxies that are too bright, stars that are too big, explosions that are too energetic. And every time we revise the models, we add new physics, we expand the range of what we think is possible, and then we build an even better telescope and find something even stranger. This is the frontier, not a line on a map, a horizon that keeps receding. The more we learn, the more we realize we don't know. The edge of our knowledge is not getting closer. It's moving away from us faster than we can chase it, and that is not a failure. That is the nature of exploration. You don't explore a place by figuring it out completely. You explore it by pushing into the parts you haven't seen yet. And the universe has a lot of parts we haven't seen. So here we are, standing on a planet orbiting a middle-aged star in the outer suburbs of a spiral galaxy containing 200 billion other stars, most of which we will never observe individually, in a universe containing 2 trillion galaxies, most of which we will never study in detail, surrounded by light that left its sources thousands or millions or billions of years ago, watching a recorded history of objects that might not exist anymore, using instruments that can see farther than ever before but still can't see most of what's out there. We have found the largest stars we know about. We have measured their sizes to the best of our ability. We have tracked their evolution and predicted their deaths. And we have done all of it knowing that there are larger stars we haven't found yet, and there are measurements we got wrong, and there are questions we haven't thought to ask because we don't yet know enough to realize their questions. The universe is not a puzzle with a finite number of pieces. It's an infinite frontier. The boundary keeps moving. The unknowns keep piling up. And the tools we build, no matter how sophisticated, will always be limited by the speed of light, the expansion of space, the opacity of matter, and the simple fact that we are finite beings trying to comprehend something that is effectively infinite. We will keep building better telescopes. We will keep finding bigger stars. We will keep revising the record books and updating the models. And the universe will keep doing what it does, unobserved and unconcerned, vast beyond comprehension, operating on timescales that make human history look like a single frame in a film that has been running for 13.8 billion years and will keep running for trillions more. That is where we are. That is the scale we're working with. And the fact that we can measure any of it, that we can point an instrument at a patch of sky 19,000 light-years away and say with any confidence that there's a star there so large it would swallow Saturn, is a testament to how far we've come. But it is also a reminder of how far we still have to go. The largest star we've found is not the largest star that exists. It's the largest star we've found so far. And the search is not over. It will never be over. Because the universe is bigger than we are. It always has been. It always will be. And no matter how much we learn, the unknown will always be larger than the known. That is not a problem to solve. That is the nature of the cosmos. Endless, expanding, unknowable, and entirely indifferent to whether we ever figure it out. Light takes 9 hours to cross Stephenson 218. 9 hours at 300,000 kilometers per second, the fastest speed the universe allows. That number is not a decoration, it's a boundary condition. It's the universe telling us that stars can grow so large they stop making intuitive sense, and the only thing keeping them from flying apart is a knife-edge balance between gravity and radiation pressure that fails more often than it holds. And when it fails, the star doesn't collapse neatly. It bleeds, it erupts. It sheds entire planets' worth of mass in a single convulsive pulse, and then keeps burning anyway, because the alternative is worse. We built telescopes to see these objects. We measured them. We catalogued their sizes and tracked their deaths. And every measurement came with a timestamp decades or centuries or millennia out of date because the light takes that long to arrive and there is no way around the delay. The stars we're watching might already be gone. The explosions we're predicting might have already happened. We are studying ghosts. ancient light from objects that existed when human civilization was still figuring out fire. And the ghosts are teaching us that the limits we thought were firm are softer than we believed. Stars can grow larger than the models said. They can lose mass faster. They can exist in states that shouldn't be stable but are, at least for a while, at least until they're not. The universe is not waiting for us to understand it. It's not slowing down. It's not making itself easier to measure. It keeps building stars at the edge of what physics permits and then watching them tear themselves apart. And somewhere out there, right now, in a present we can't see, another hypergiant is collapsing. The core is falling inward, the clock has run out, and the light from that collapse is on its way. It will travel for thousands of years through empty space, carrying the news that something impossibly large has finally broken. And when it arrives, we'll point our telescopes at the sky and say we discovered something new. But we didn't discover it. We just finally caught up to what the universe